Good morning. I can't tell you how good it feels to hear that. Like, welcome back. Show of hands. Is this your first Monitorama? Did you not get the memo? I'd like to welcome you very much. It's my pleasure to have you here for Monitorama Portland 2022. As you probably noticed from your ticket 2 or 3 years ago, this was supposed to ship back in 2020, but at some point you just got to call it good enough. Reminder, thank you everyone. I know, we're still trying to come out of this pandemic. I appreciate everybody, going with the policy, getting your vaccination checks. I do see some folks not wearing their masks in the audience. Please put your masks on. Let's keep them on as much as possible, especially in this theater where it's kind of an intimate environment. I appreciate it. If you're missing your Slack invite, if you still don't have it, shoot an email to info@monitorama.com. Make sure to take care of that. I think we've got most of the stragglers fixed. Wi-Fi, we have Wi-Fi here. It's the Monitorama Guest, which is public. It does not require an SSID, so feel free to use that. Please don't download, videos, live stream, etc. If you want to live stream, you want kind of a space, you want to get away from the main theater for a little bit, we have space on the 3rd floor in the rehearsal hall. We have the live stream running there. You're also welcome to go out to the lobby, or if you want to step away and go to your hotel or anything and watch from the live stream from there for a bit, that's fine too. A reminder, no food or drinks in the theater. Quick question, did anybody get pour over from the coffee stand out there?
That stuff is awesome.
Okay. If you weren't around for PDX 2015, you might not recognize them, but the 2 baristas on staff are actually my kids. So that was kind of cool. For years, we've had Nosa Familia actually provide barista services. They would do pour-overs, they would do cold brew on site. Obviously, that's one of the things that kind of fell to the wayside during the pandemic. But a big part of my experience in Portland is bespoke coffee, really good coffee. So I wanted to continue that. So props to my kids for making that happen. Bathrooms. If you're looking for the bathrooms, there's a big restroom. Big restroom is 1 floor down in the lower lobby. You can get down through the stairs or through the elevator. There is a single stall ADA non-gender specific bathroom, or they are single stall ADA non-gender specific bathrooms. 2 on the main floor off the lobby, one floor down off the lower lobby. If you haven't already seen it, which hopefully you have, please review the code of conduct off the main website. Let me know if you have any questions or concerns about that. And a quick refresher on our schedule. So over the next 3 days, we have 30-minute talks throughout the day. In between 2 of the talks twice daily, we have 3 5-minute sponsor talks. Sponsors help make this event possible, so please show your gratitude and appreciation for them when you can. We have 30-minute breaks, 1 in the morning after the first 2 talks, and then another 1 in the afternoon. And then we have a very long lunch. We have a 1 hour, 45-minute lunch. There's a ton of great places nearby to grab lunch. If you haven't seen it already, join the lunch party, and props to anybody who gets the Office reference, in Slack. I've actually pinned a Google Map list of all the places that are available locally, that are super convenient and have really good food. And I guess if you got socks already, you got a ticket, ticket in the back of your badge. Hold on to that. We usually do raffles at the end of the event. And don't forget about the after party this evening, Castaway Portland. It's northwest. It's easy ride up the NS line. You can take a scooter, you can take a bike, or it's walkable. So please join us between 7 and 10 p.m. And I think that's it for now. So I'm going to hand it off to, if you haven't met this guy, Mr. Pete Cheslock. He's been around for a while. I think he's given a couple of talks at Monitorama.
Yeah, pre-COVID hair. So
Yeah.
If you're like, who's this long-haired hippie? That was me. I talk about ships sometimes.
He's actually going to be helping with the MC duties, so he's fantastic. He's a great friend, and please treat him, accordingly.
That's not a good sign.
Anyways, thank you very much. I'm going to go ahead and hand it off to Pete and our first speaker. But again, thank you for being here, and have a great week.
It's really great to see so many first-time attendees to the event. I've been to every Monitorama in the U.S. I'm actually wearing a T-shirt from the first Monitorama from a sponsor who I guess still exists as part of another company. We'll talk about them later, actually. So I don't like long intros, but our first speaker is someone who is winning the prize, or at least coming out in the lead for Best Dressed at Monitorama, Corey Quinn.
Thanks. I'm just going to enjoy and bask for a second here. It's been a long time since I was on stage in front of the community. My first Monitorama as well, and I miss this. Okay, that was for me. Now let's do it for you here. In 2014, James Mickens took to the Monitorama stage to deliver an absolutely transcendental talk called "Computers Are a Sadness and I Am the Cure." I am very clearly not James Mickens, for those who are a little slow in the uptake there, but his speaking style stepped off of the stage and into the pages of legend. And I aspire to one day be a legend of my own, or a cautionary tale at the very least. So now that you have the context for the talk, let's begin. So, this talk is called Build versus Buy, the final showdown. And the reason is because I asked Jason Dixon what topic he really wanted to see a talk about. That is a pro speaker tip for how to get a CFP accepted, in case you're wondering. And his answer was, I'd like to see a talk about build versus buy, because he is professionally very sad all the time. So I ignored it. And the real title of this talk is instead, Monitoring is Expensive and I Am Obnoxious, because it is and I am. Now, I want to set the stage here a little bit and give a little context of why I'm talking here. I'm a consultant, and I have absolutely nothing to sell you. The one thing I consult on is AWS bills. So if you call me for anything else, like production is down, like, oh, wow, that sucks, and then I hang up the phone. It is glorious. It is the best kind of problem. Someone else's. And I also, because I'm a consultant, all our systems are internal or a marketing site. I don't have a production infrastructure that I care about. You know, kind of like an SRE who's way past the point of burnout. So I sleep the sleep of the just at night. I exaggerate slightly, I have young kids. But what this means is that I get to insult absolutely everyone in this room all at once because I have zero skin in this game. I don't have a horse in the race. And that's glorious. I'm insulting you all from the cheap seats. I didn't imagine that the cheap seats were on the actual stage, but, you know, life continues to surprise as we go through it. So let's pretend for a minute here that you need to do something really complicated, like, I don't know, monitoring something. And you, in this case, are my erstwhile companion and mascot, Billy the Platypus. So let's dive in. And immediately, you're confronted by a choice when you need to implement that expensive, confusing thing. And Jason asked me to talk about build versus buy as we get into this, and that always seemed like a false dichotomy, because remember, I work with AWS bills. CloudWatch is always there, it's really expensive, so you're buying something, and you have to build a shitload of stuff around it to make it in any way useful for anything. So it's like, why not both? Both seems like a good idea. But that's a separate problem. I would like to reiterate as well that this talk is entirely Jason Dixon's fault. So here's the talk you asked for and thought you wanted. I don't think you're gonna like it very much, but I assure you it is far too late to stop me now. I would also like to start with an apology to all of the vendors I am about to name. I am not picking on you specifically, but you have been included for the very best of reasons. Your logos were convenient. Thank you for sponsoring this conference. Okay, so you have to build versus buy, because the time has come where you as a company or as a manager, or God forbid as an engineer, have to decide between this, and you're going to build a business case for it. I know, you exclaim, I'm going to do a total cost of ownership analysis. And I want to start with an uncontroversial position that TCO analyses are bullshit, because they're all trying to sell something, usually badly. They're all inherently made up. They are a justification exercise that backs up a point that someone has already made. They're predetermined by whoever is presenting the thing in the first place. There's no such thing as an objective TCO analysis. Has anyone ever seen one? where the analysis does not agree with what the person putting it together originally wanted to do in the first place? No, you have not. And yes, that was a rhetorical question. So on the one end of the spectrum, yeah, you have people saying, oh, buy, because they're inherently trying to sell something, which I get. Buy my company's product. And yes, that is a screenshot of the sponsor list for this very conference. Awesome. And right before I went on stage, I couldn't help but notice that it is not lost upon me that my business partner signed our own dumb little company up as a sponsor, which kind of eviscerates my point. And after this talk, he will be getting the hose. I digress. So you have vendors over in the buy corner. But now, on the other extreme of the spectrum, you have engineers who are basically justifying their own jobs on some level, or at least that's what it feels like. What they're selling is, please don't fire me and replace me with a vendor product. It comes down to bias, because bias is inherent to every one of these analyses. Let me show you some that we have all seen again and again and again in a whole bunch of different contexts. So let's say you have an analysis, and it seems that build wins. Awesome, makes sense. But very often it underestimates the staffing expenses. Maintenance, ongoing maintenance of these things is very rarely calculated in. And there's loaded costs of this stuff too. It's not just, well, what do people make in salary? It's what is the loaded cost with all the benefits, the office space, the office supplies that we all embezzle from our employer, which got really hard during the pandemic, but not impossible. And of course, opportunity cost, where when you're building the monitoring system, you're not doing other things that are valuable to the company as well, unless you're a monitoring company. Yes, I know, there are probably better rooms I could make that particular point in, but cool, let's pretend. We also talk about, they always lowball the cost of scaling these things. Like, oh, we don't have to deal with short-term retention of data. We can have infinite retention and conveniently omit the actual storage cost of storing all that data in perpetuity. And it winds up also, forgets the cost of, as you continue to grow, you're going to be adding in new capabilities left and right. It's never set it and forget it, as much as we like to pretend otherwise. And of course, everyone invariably winds up just mopping the floor with some vendor that is stood up almost like a straw man argument. But, you know, whenever vendors complain about that, they're accused of being self-interested. I'm not, I just find it unseemingly. So that's what happens when you wind up dealing with a world where build wins. Let's look at the other end of the spectrum where, we're going to buy these things instead because that's better. Well, what do you see there? Well, a lot of the third-party costs tend to be overlooked entirely. Oh, just ship all your data to us. Great. Well, I can look at the cost of what you're charging me, but I'm in a cloud provider. Data egress is a thing, I promise. If you don't believe me or aren't aware of that, oh, are you in for a fun surprise later? Also, they tend to overestimate the sheer amount of time and energy it's going to cost for in-house. Like, you're going to need to hire a team of 20 people to build a monitoring system. Citation very much needed on stuff like that. It also wildly tends to underestimate implementation costs. It's just, it's so easy. You just click a button and it rolls out to production. Sir, we're a bank. There are a few more steps and boxes we have to check, and for anything even slightly complicated, it has to be integrated with a lot of the applications that you're deploying as well. It is never that easy. And of course, they tend to also do fun things, such as, assuming that the great deal you're getting for year one is what you're going to be paying in year 2, 3, and 4 once you're bought in. Spoiler, it is not. And I get why this happens, but you often over-rely on the very prettily done TCO analyses provided by the vendor as part of their pitch deck, because they've done a lot of these things, and they, of course, are never going to give you anything that says, wow, it turns out we are terrifyingly expensive, buy something else. And it's easy, but it tends to over-rely on that without questioning it too well. My point is that you should be telling a capability story. That's why you're going down the path of whether you build or whether you buy. But that isn't what happens. It never is. Instead, you are making a decision and then backfilling an analysis to justify it financially. And I have never seen this not be true. So as a result, TCOs are inherently bullshit. All of them. And sooner or later, someone is going to realize that applies to other sorts of TCOs too. Like, are you saying the cloud migrations TCOs are not correct? That's right. They're bullshit. They always are. It applies to all of them. So that's how we get there. But regardless of which side you choose, you are going down one of two paths, build or buy. Let's explore the first one of building it out ourselves. Vendor products, well, they suck. And we are special and unique snowflakes. Because I am an engineer, damn it. And if I wanted the most interesting thing about me to be that I cut large checks to companies I don't know a lot about, I wouldn't be an engineer, I would be a VC instead. Now, when I say build your own, we're really talking about two subcategories here. We're either going to take a whole bunch of open source tools and then glue them together with duct tape and baling wire and more than a little bit of hope. And otherwise, we're going to wind up building our own bespoke system internally from scratch. That's also known as the we did it better at Facebook method. Because you've decided at that point that absolutely nothing in the open source world is going to meet your very specific needs. That's almost never true. Facebook's problems are not your problems. They have different ones. Because what you're doing in almost every case is you're not solving innovative, groundbreaking, world-spanning scale. You're doing resume-driven development. Let's be very honest and call that what it is. You are overcomplicating things for your own career advancement. And that's a bad plan. Incidentally, overcomplicating things for career advancement is, in fact, the tagline and origin story for Kubernetes, but that's a talk for a different conference. So if you're cobbling a bunch of open source stuff together, what are you doing exactly? Because almost all of those open source products do have paid offerings by companies that specialize in it. Is it that you're cheaping out? Is it it's purely about cost for you? Because let me remind you, this is not something that you're doing in your spare time. Contrary to popular opinion, the $400,000 a year observability engineer is expected to provide more value than arguing on Twitter about what observability means to them for 16 hours a day, one would hope. Your time is incredibly expensive to your employer. It is always more than the infrastructure itself. The engineering instinct in all of these cases is to build things, and I get it. I'm not saying it shouldn't be, but make sure that you're building the right things that get your company to its next milestone. Because I gotta level with you, talking to a whole bunch of the SREs who really like to index over on building these things out, I think you really want to build a monitoring product instead. And I'm pretty sure that this statement, while true, is also going to be a personal attack to an awful lot of you. But look around at all of the monitoring companies we see sponsoring here, exhibiting, and we're implementing in our environments. How many of them arose almost by accident based upon how they did monitoring at their last company or how they wished they had done monitoring at their last company? And speaking from the customer side of the fence, the Cambrian explosion of different tools in the monitoring observability space makes being a customer worse, not better. Nothing, be it a vendor tool or something you built yourself or in the open source world, is going to do a great job of talking to each other. Despite the industry's best efforts at being interoperable, a lot of these things have so far to go. I mean, the OpenTelemetry project, great idea, but I haven't seen it work yet in anything remotely resembling a workable environment. It sounds great, but it works in theory, not in production. Incidentally, theory is the name of my staging environment for that exact reason, but that's neither here nor there. Netflix is a good example of a company that takes building it yourself to an extreme. Because they're now a $30 billion monitoring company that gets paid for streaming movies, and okay, great. In 2015, Netflix was spending 6 figures a week on observability. I learned that little factoid from a talk they gave at this zany conference called Monitorama a while back. Stop me if you've heard of that one. And they're Netflix. They evaluated their choices, and they were happy with them. I mean, who am I to say that they were right or wrong? Would they do it again the same way in 2022? God, I hope not. But they chose where to spend their creative energies. Any company has a limited number of things that they can meaningfully invest in to innovate on successfully. And I would suggest that you think, that you really put some thought into and be honest with yourself in the process of whether or not building monitoring tools or cobbling them together from spare parts is one of those things that is core and central to your business. So that's build. Let's instead talk about buy. And let's be clear, it's never phrased as, oh, let's go buy something instead. It's usually, let's go buy product X. And maybe it's because someone has used it before. Maybe they got tackled by an overly aggressive badge scanner at a conference somewhere and just sort of fell in love with the awesome swag or whatnot. We're never going to know for sure, but they're clearly playing favorites. When they have other competitors, they're often brought in as at the last minute to make it not look like the no-bid contract that it pretty much is. It's fun, and there are reasons to buy, though. I mean, who here has pre-ordered the latest SRE book that's dropping soon? Anyone? Cool, at least I assume that it's an SRE book, just based upon the title alone. Because a key tenet of SRE, which comes from the Mountain View region of California exclusively, otherwise it is just sparkling DevOps, is that nothing is ever an engineer's fault. Now, it's sometimes hard to sell that vision to management, which is why vendors are so critical. For only a staggeringly large pile of money, you can throw them under the bus instead of yourself. If it didn't work, clearly you didn't have the right vendor in the right spot of the 15 companies you're slapping together to build these things. Because it's important, don't you know, to approach observability from a position of composability. Now, what do I mean by composability? Instead of one tool, you use a whole bunch of individual fit-for-purpose tools. The problem is, in the fullness of time, people start asking them to do more, and those people are often not customers, but investors or the market, and they want them to do more things. And as a result, you wind up chaining together a bunch of what look like multi-function printers, where, well, we have that one because it's the best at faxing, and that one is super great at scanning, and who's happy here? And of course, all of these vendors are asking for the same slice of your budget, ignoring that they are very far from the only company and product that you've got to buy with that stuff. And as a result, you have multiple products from vendors, none of whom are willing to admit, much less entertain, that you are going to need multiple vendor products for different things. And you wind up with a complete and total mess. Remember, I'm a cloud economist. I see the results of this unfolding on the AWS bill. See, here's what you think is happening, where, oh, we just wind up pulling these things out of CloudWatch when it's in AWS, and then we basically slice and dice these things. Yeah, here's what's actually happening. Each vendor is doing its own relationship, its own things, and when it shows up on the bill, and CloudWatch is your #1 most expensive service in all of your accounts, it's usually something like this. Because the best part of all of this is that none of these things work together. They claim to be interoperable, don't get me wrong, but CloudWatch charges per request. And all of these products are making completely independent use of staggering numbers of CloudWatch queries. So what you hope is happening is that a single CloudWatch fire hose is being consumed by all of these vendors. But what actually happens is there are 5 incredibly expensive burning piles of money that are being consumed at once. And good luck tracking down which one spiked last month, because, spoiler, it's not easy. And lest you forget, despite their most fervent wish to the contrary, Amazon is not the only vendor that you're paying for things. I know they have entire teams of people working on this because their product strategy is yes, but they're not there yet. So other vendors clearly want their cut too. And before long, you are spending more on observing the product than you are on building the thing. And we all love negotiating with our cloud provider every few years, but just wait until you get to negotiate with the dozen observability vendors that you have who all pretend that they're your only vendor. That's not a fun job. So where does that leave us on the build versus buy discussion here? It leaves it as a whole bunch of different things here, because it's a problem. If you wind up building, your cost is going to rival the gross domestic product of Belize. It is going to involve so much wailing and gnashing of teeth due to complexity. And of course, you'll get called out by talks at Monitorama for doing it wrong. Whereas if you buy, it will cost roughly the same as the GDP of Belize. There's going to be a lot of wailing and gnashing of teeth. And of course, you'll get called out by talks at Monitorama for doing it wrong. Simple, right? So where does that leave us? Well, it's not about cost. I know, weird thing to say as a cloud economist, but it's true. It's a strategy and a capability story. And because I don't have anything to sell you, well, that's your problem to deal with, not mine. This is probably the most honest slide you're ever going to see at a conference. Mark this day, because it's true. It absolutely is true. There's no way to avoid it. As much as we have to pretend otherwise, we are doing the best we can with what we have. So do I have an answer for you? Well, James Mickens would almost certainly have a better answer for you. I mean, look at his title of his talk. I am the cure is what he said, because he is James freaking Mickens. And I am not. I am the shitty version of James Mickens that nobody actually wants but claims to be able to deliver what he can. I am Amazon Basics James Mickens. I am only barely fit for purpose here. And I don't have an answer, and you're all screwed. I am Corey Quinn. You have been a great audience, and welcome to Monitorama. I will not be taking questions. I will not be taking questions. Have fun.
Love you, Corey.
All right. Wow, that was a lightning speed talk from Corey. I had a whole 5 more minutes. So we're just going to get our next speaker set up. And because Corey was super fast there. So who is first time in Portland? Wow, a lot of people first time in Portland. Who got in last night on a delayed flight? I want to figure out who had the longest. So I had a 3.5 hour delay. Josh, who's in the audience, was also on my flight, so you don't count. Anyone beat 3.5 hours? What do you got? 12 hours? Oh my goodness. That is terrible. Can anyone beat 12-hour delay? They were actually offering $1,000 for me to catch the next flight, and about 3 hours into my delay, I really wish I took it, so. All right. All right, everyone, let's give a big round of applause. Wait, because it's not happening yet. Nope, no applause. Oh, we're so close. Slide. Yeah. All right, now that we've got the presentation working, nice big round of applause. Kick us off.
Good morning. Can you hear me? I need to lower it. Can you hear me now? Okay. Good morning. How's everyone doing today? The little SLI that could, that's the name of this talk. By Sophia, that's me. I'm not sure if you're familiar with the story of the little engine that could, so I'll give you the TLDR, as they say. This story is about a train that brings candies and treats to all the little children who live just across the mountain. One day, the train is chugging along, but then its engine suddenly wears out. The toys and train ask for help. A snazzy new train passes by and says, "Sorry, bro, I'm built from shiny new best practices. I can't help you." So it goes smoothly up the mountain on its own and disappears. Then a big freight engine shows up. Gruffly says it's too important. It has one job, it does well already, so it won't help. And it goes over the mountain and disappears. Then the toys see this little blue engine coming near. In the story, it's a she. The train and toys are hopeful that she'll help. She's small. She isn't sure that she can do much, but says she'll try. And she tries, and surprise, surprise, she does it. The little engine delivers the children all their treats and toys, and they were happy. That stop motion was really fun to make, and it took a very long time. But the goal of today's talk is to talk about what implementing SLOs look like for us at Betterment. I work at Betterment. I didn't mention that. I should mention that. We're also hiring. More specifically, it's about how we gathered our SLIs. But before we get there, let me introduce the context in which this conversation about SLIs even came about. A few givens, if you will. Writing good code can be hard, right? By good code, I mean well-documented, well-instrumented, well-tested code. It's hard. SLOs, they're also hard. That's not particularly profound, but this is one of the driving points of a lot of the work my team and I have been doing the past couple of years. Choosing the right SLI is a complicated matter. I'm here to talk about how we chose some SLIs and how choosing perhaps the most generic ones worked well for us. This is a story about how my team tried to make choosing SLIs and crafting SLOs as easy and frictionless as possible, and how this approach was influenced directly by how we built out our CI and CD pipelines and the rest of our platform. I was really intimidated by SLOs for years. I felt like it was this big, daunting thing that only geniuses at Google could implement. But then I realized that SLIs and SLOs are just tools. And tools are not merely valuable things to fuss over. They are meant to help people wield changes in the real world. Everything we're trying to do here is intended to help humans deliver goods where they need to go. So by reframing the problem to how can we help engineers, humans, collect the right information so that they can best do what they need to do in the world, I was able to make some progress. And so I hope that our approach might inspire some other folks who've been just as intimidated into believing they could never make progress. You can do it. A couple years ago, it started to become apparent that the engineers at our org wanted to start prioritizing performance, to start focusing on data-driven development instead of building from Figma designs and calling a feature done by how well it matched the original UX. They wanted to design their features with proper instrumentation. Different teams tried different things to solve these problems, which led to solutions that were almost impossible to replicate across business lines or teams. And yes, when I search back in time since 2016, the majority of messages about SLOs and SLIs originated from me, but that's neither here nor there. So we took our learnings from how we designed the rest of our platform, where we prioritized standardization over infinite feature sets, ensured principles drove the design. Opinionated frameworks come with pros and cons, but by eliminating certain choices, they actually contribute to faster development and better engineering efforts. Engineers can focus on doing what they need to do. John Ousterhout, I think, talks about this in his philosophy of software design. Focus on eliminating complexity as a means to good, solid design. And last but not least, ensure a faster development feedback loop. Constantly iterate to break through, which is a central tenet of Betterment's philosophy. So the state we were in was lots of teams tried lots of things in the past, which meant observability solutions were varied. Having so many different ways of instrumenting code, creating monitors and dashboards, according to how team vibed, resulted in dead alerting systems when folks would leave the company, one-off monitors that couldn't be easily replicated for new apps or systems because the discoverability was limited due to how Datadog presents its resources. This approach reinforces tribal knowledge, which isn't how you scale. I mentioned this already, but for our observability needs, we use Datadog. I love Datadog. The main problem here has been that there's just so many knobs and gadgets to play with. It takes quite a while to understand how to interact with it. My team might be Datadog pros at this point. We're SREs. It's kind of, we're pros at everything, kind of, but in a minimal way. But a new engineer might have zero idea of how to find an alert, let alone create one. We needed the right abstraction to hide the complexity of Datadog. Prioritizing standardization has driven my team's philosophy for some time. Keeping the interface to different systems, CI, CD, data pipelines, logging, dashboarding, package management, the same across the board, and keeping the output the same across the board, but obviously allowing flexibility when needed. It's allowed our really lean SRE team to build a lot of really powerful tooling for over 100 other engineers. Given that everyone's interactions with Datadog was so unstandardized and so widely varied, it became clear to me that this project of the SLI and SLO tooling was not just about a standard interface, but also about reducing the complexity of the developer experience of observability tools. So I took what we learned with our other systems, and I thought engineers just need a standardized way to instrument their code, a standardized way to alert on their code, and a standardized way to keep tabs on their code over time without stressing themselves out all the time. So yeah, they need SLIs, they need SLOs, but they also need a simple way to create, manage, and discover them. My first approach was useful, but perhaps not the best. My goal of this talk was to share the journey, so that includes where we stumbled. I jumped straight to custom metrics because these always seemed, from a code hygiene point of view, to be the strongest way to represent an accurate picture of the user experience of a specific domain. So I thought, let's wrap some micrometer and statsd classes with a bit of syntactic sugar to make it easier to emit custom metrics in a standardized fashion, to make the tagging consistent for those power users to do what they need to do with the information. And I'm not sure about you, but this had as much success in legacy code bases as asking a new mother to sleep when the baby sleeps. Super important, right? But somehow really difficult to do. Asking folks to go into legacy domains and instrument consequential methods aligned to critical user experiences with custom metrics wasn't going on anyone's roadmap easily. New Rails engines, new Java libraries, forget about it. Clean slates means you can use all that new hotness with ease. Any new projects were properly instrumented and statsd and all of that. But what about that rusty old engine or that big freight train with one job? And what about our sluggish little engine that's still stuck, waiting for help? Teaching people who are contributing to legacy code bases how to use the right statsd methods, how to use active support notifications, how to add micrometers to their classes, when they could instead just be writing their normal, well-documented and well-tested code, it didn't have the rate of success I imagined. And so I learned that to get teams on board with this new observability-driven development approach, we'd have to facilitate easier instrumentation. And I know what you're thinking, statsd isn't hard. It's not that the concepts were difficult, it's that legacy code bases are difficult to instrument after the fact. And I know a lot of companies are like that. A lot of startups that are, have to get product market fit quickly, and then they become successful. They don't have the best history of observability. And that's why we're all here this week. We're trying to change that. So we went back to the drawing board. Power users were happy, but few and far in between. It was a new engineer with a very busy engineer who just wanted to keep tabs on error rates and latency for their code. And it was those people that we needed to help. They didn't want to spend days or weeks out of a product cycle focusing on performance and telemetry and solving those problems. We needed to find a way to slide in SLI collection with the same ease that RSpec, for example, provides a testing framework. Without a framework, an engineer would have to go into Datadog, figure out the right query, or find the right suggested monitor creation button on their APM page, and create that. And then if they ever left the company, well, that might go silently off into the ether of some abandoned Slack channel. And ultimately, the complexity of Datadog was deterring folks from doing much with it. And we had the same problem with Splunk and New Relic before that, so I'm not trying to harsh anyone's mellow. Before we could solve anything with more tooling, we need to really define the problem space. Observability as the problem isn't super well defined. We knew we'd need a way to reduce the complexity of engineering's interactions with our observability system. People wanted to prioritize performance, but it was such a drag that all the teams couldn't do it in a sustainable and consistent way. And so we also knew we would need to ensure consistency in those interactions through a standard interface of some kind, like I've mentioned. We also definitely wanted to eliminate the abandoned dashboard, abandoned monitor problem. To make sure we weren't solving a problem no one asked us to, we'd have to validate it first, which didn't take long. The question of which team owned an app or an alert was an oft-raised one. So we were able to simplify the problem space to code ownership and code accountability. And I was thinking mainly about how to provide a solution to this in a frictionless way. Another engineer and I chatted and thought about how we could do this in the simplest way possible, which really meant go to the code. We mused on the idea of creating some kind of code-level keywords that we could introspect the code base for during CI or at deploy time and then just do something with. This would be something we could lint on, and thus ultimately require. We thought, how can we make it easier for engineers to automatically know they own something, and also that the thing they own needs to function in a certain way? We were already doing this with background jobs through a simple Ruby method called job owner, the value of which we used to find a Slack channel for notifications. We'd inspect a YAML file, send alerts to whichever Slack channel matches the job owner. It was pretty lo-fi. It seemed like we could mimic this, but I knew that we'd probably need some more configurable options than a Ruby method, which just didn't seem structured enough. Someone might easily forget to add it since it's just an extra method. I knew I'd want to have a corollary solution for Java folks, so we decided to go with the keyword annotation combo. Here's the Rails one. It would have to make sense in the Railsy context, so of course it corresponded to different actions and mirrored Rails class inheritance. We provided reasonable defaults for everything, so you could theoretically just add owner, SRE, and our code handled the rest. The Java one matched in functionality, but led with the concept that it was explicitly for monitoring, since there weren't as many Java subteams as there were Rails teams working in a single code base, so ownership wasn't as much of a problem. They also had their own internal way of defining reasonable defaults, which of course resulted in like 4 other really very big verbose classes that I won't bother putting here because #Java. So back to the implementation. The interface needed to be simple, but the internals, well, that can be as complicated as it needs to be. And this is a complicated diagram. This is a workflow of how we use those code annotations to create SLIs. At deploy time, we'd have a rake task or a Gradle task. Eagerly load all the classes in the codebase, find all those instances of owner or Datadog monitor, coerce all those options into JSON blobs, and then print them to a file. Our CD CLI would then load the file, validate it, send it to a web app API that would then create database records for the JSON blobs, blah, blah, blah. And then monitors would be created in Datadog. For every annotation, we would create monitors for latency, change in throughput, high error rate, and new errors for a latest deployment. And because it was version 1, and because you always make mistakes the first time, we would automatically Slack you if those monitors had violations. And I don't know about you, but latency monitors can go off frequently. So I thought, how can we let folks alert on their most prized possessions, their API endpoints, but also not destroy their sense of hope and accomplishment every day? We knew we wanted guaranteed coverage of code with monitors, so we just defaulted to false for slacking and paging and allowed those to be configurable for power users who really wanted to know. But we needed to do something with all those alerts that we now had. So the pièce de résistance. I knew SLOs were theoretically the solution to this, but this V1 of tooling happened in 2019. I'd been to talks about SLOs, read the Google SLO chapters, had this gut feeling they were the answer, but I didn't know how to do them. We focused on getting the SLIs created, properly tagged and standardized, and in the fall of 2020, Alex Hidalgo's book, Implementing Service Level Objectives, came out. I don't know if he's here. He must be here. He's giving a talk. I saw our next steps. I consumed that book faster than an Instagram feed. I was in love with it. It was so accessible. He outlined everything. And what I saw was a bunch of rules, not that they actually were, but I love rules. I love a framework any day. Rules and frameworks to me are the tools to help make change in the real world. I made a strategy doc like he recommended. It had a fancy table of contents at the top. I got buy-in from all the higher ups. I started writing more tooling to go along with our SLI collection. I was given the go-ahead to craft workshops and work with teams directly to think and implement service level objectives for their services. I was on a mission. I was also at the end of my second trimester by the time I started these workshops, so there was a deadline. The folks that participated seemed to really enjoy the workshops, but it was hard to scale. It was difficult to get teams to dedicate a few days off their product roadmap to learn about SLIs and SLOs and actually implement them using the new tooling. So what's the answer to a human problem? Ours, at least, was to make the tooling even more self-service. So we'd already created an SLOs repo separate from the application code as part of the tooling. This was to enforce standardization, simplify the interface, prioritize discoverability, and decouple target SLO goals from application deployments. If you wanted to change your SLO from 98 to 99% coverage, for instance, you shouldn't have to rebuild and deploy app code. The SLOs were organized by repo, squad owner and service, and it was all in YAML because SREs love YAML, with an accompanying markdown file that required folks to fill out descriptions of the chosen SLIs and the plan for revisiting and all of that. Datadog supports two kinds of SLOs, metric and monitor-based, so we supported two kinds of interfaces. Here's the metric one. You just plug in the right query. This was for our power users who are already implementing their code with custom metrics. Monitor SLOs were the most frequently one because they were the simplest to implement. You just plugged in the monitor IDs from your automatically created monitors from the owner or Datadog monitor annotations, and voila, there you go. So once you merged a PR of your new YAML file into the SLOs repo, that same CLI would ping our web app, and it would handle upserting the SLO in Datadog with your details. But there was another problem. You'd have to go into Datadog to fetch the ID of a monitor that was created automatically, which felt cumbersome. So that friction of plugging in monitor IDs led to V2 of the owner Datadog monitor annotation work, always iterating to breakthrough. We decided to support two new features, feature and tags. Tags were again for those, 6 power users, but this time we added feature so that those that aren't power users could more reasonably associate DJ and controller monitors with SLOs. Of course, we can't forget our Java friends. So now you just put in the tags you added to your endpoints, and for this category and this feature tag, we create an SLO using all the latency monitors we've created for your controllers that match the feature add goal. And this is how it looks from a bird's eye view. Annotations map to monitors, SLO YAML maps to SLOs. And here's how we support discoverability. In addition to the SLOs repo, for those who might be on the product team and less entrenched in GitHub, there's a metrics section of our application platform. And yes, we built it, we didn't buy it. And we surface links to all your annotations in Datadog and all of the relevant information for your SLOs. The best part about this is that it worked. I came back from 6 months of maternity leave. I asked around about how the SLIs and SLOs worked for folks, and they did. For the folks who'd written their SLOs and turned off noisy alerts, they're actually able to allocate resources appropriately. Everyone knows SLOs work, right? But they can even work with what I'm calling a bit of lazy SLI collection. I was so focused after reading Alex's book, I don't know where he is, but can I call you Alex? The importance of getting absolutely the right SLI. It's critical to real SLOs that match our user experience, right? You can't futz that. But you actually kind of, sort of can, I found. What's next? Well, of course, we're going to keep improving our SLI collection. The best way to get as close to the user experience as possible is through client-side SLI collection. We have a plan for our React components to match our owner annotations elsewhere. What I've learned during this exercise is that it really does take quite a long time to transform the culture at an org with over 100 engineers, over 50 engineers. It's hard, and of course we're not done. Making it easy and simple to annotate your code and collect SLIs the way that we've done, it's really facilitated this journey. It's 1 or 2 steps away from automatic SLI collection, which I don't necessarily recommend, but it's a couple steps removed still from SLI-driven design, but we're getting there. So to summarize, engineers like to write code. They don't necessarily like to go back and instrument legacy code for performance reasons immediately, but yes, eventually, obviously, for very critical, important business things. Engineers need to instrument their code. Engineers need to write SLOs. Engineers like frameworks. They like routine. So we gave them a framework. We gave them a tool to wield to help them do real work in the real world. Thank you. That's all I got today. This is me on Twitter.
We got these speed speakers today. I keep letting them all know. When you have 5 minutes left, I'm going to hang out down here and wave or like awkwardly whisper behind you. And I have yet to get to that 5-minute time. All right, so right now it is a little before 10:30. We're going to start our break time. 11 o'clock is where we'll kick it off back in here with our next speaker. So head out, grab some coffee, Make sure you tip Jason's kids. There's one of them in college and one soon to go to college, so like support their college fund. It's great coffee. And we'll see you back here at 11. Thanks, everyone. hopefully tip well. Again, they're going to college. All right, well, next up, so real quick, actually, before we introduce our next speaker, I'm going to see if I can. So after our next speaker, we're going to have our 3 first sponsors. Again, make sure you get around to visit the sponsors. They do help support this. We're going to have the Sensu/Sumo Logic folks, VMware, and Big Panda. So you should already know you're presenting, but please meet me on stage here in about 15 minutes to the sponsors. So, all right, with that being said, let's kick off this next round of talks. And I'm going to introduce up here Steve Flanders.
Hello, everyone. All right, I'm here today to tell me how to DIY Ollie. This is actually a talk that I wrote a while ago, and while I was kind of revamping it for the conference, I realized that it uses a bunch of words that you may not be familiar with. So in order to make it a little bit easier, I'm going to give a better kind of working title here. I'm actually going to describe the terms as we go. But basically, it's how to collect observability data with the OpenTelemetry project. So I want to make sure I'm not using any TLAs or 3-letter acronyms or these lovely abbreviations. I'm not sure what other term to use for TLA here, but the terms here are all going to be defined. I'm going to walk you through how it can really be made a lot easier using this project. So my name is Steve Flanders. I am a Senior Director of Engineering at a company called Splunk, which is in the monitoring observability space. I have over 10 years of experience in this space. My teams work on the OpenTelemetry project. Doing this at Splunk, and prior to that at a stealth startup called Omnition that Splunk acquired about 3 years ago. Prior to that, I was at VMware working in the logging space. So I've done all the traces, metrics, logs type aspects for both open source, proprietary type solutions. So first, Ollie, as it's pronounced, the letter O, number one, letter Y. Why is it called Ollie? Well, it's because observability, between the O and the Y, there are 11 characters. So it's basically an abbreviation of the name. This is very similar to Kubernetes, often called K8s. But just knowing what the term isn't really sufficient because the term observability is often overused. So I wanted to give a working definition for this presentation. And so the definition that I'm going to use is kind of the ability to ask unknown questions using telemetry data, so think things like traces, metrics, and logs, in order to solve availability and performance problems in your environment. Now, why do you need it? Well, the answer is kind of, it depends. Like, if you're using a monolith, then maybe more traditional monitoring, and I'll describe the differences here in a minute, would be sufficient. But if you're dealing with distributed systems or microservices and you have a lot of complexity, just because you identify a problem, identifying the root cause or the user impact is actually a lot harder. And that's where observability can really help. Now, how do you get observability? Well, first you need to collect a whole bunch of data. And you might have heard of the 3 pillars of observability: traces, metrics, and logs. These are just data sources. Like, this is the types of data that you need to collect. And then you need to be able to store this, query it, alert on it, visualize it in order to solve some of these problems. Start asking questions, basically, of the data. And that's what we're going to talk about today. Some people may know that I'm actually pursuing an executive MBA right now at MIT. I actually just flew here directly from class. And we were talking about something that was more management in topic, but it actually felt very relevant to kind of distinguish the difference between monitoring and observability. So this is a model where you basically have simple problems, complicated, complex, and chaotic problems. And what do you do in those circumstances in order to resolve an issue? And your approach is actually different depending on the type of problem that you're experiencing. For example, for simple problems, you often just need to categorize it and then you can go resolve it. Versus like chaotic things, you want to act. For example, if all of production is down and all of your customers are unhappy or you're losing a lot of money, it doesn't matter what the root cause is, you just want to get your services back online. You want to act, and then you can go analyze later. So depending where you are kind of on the journey of problem space, your initial reaction is going to vary. This is also kind of true for monitoring and observability. I like to think of more simple or complicated problems as being a monitoring issue. Whereas for, let's see, we lost the display. I didn't do anything. No? Doesn't like me. We need to get some observability up in here. Let's unplug and try a different port and see if we get a better result. Sadness. I don't know. I didn't even touch it.
Turn it off and on again.
I did. Hey! I'll try to be gentle with it. We'll see how we go. So for simple or complicated issues in your environment, oh, sadness. Literally didn't touch it. All right.
Is it just I need to stand here awkwardly?
Maybe. We'll see. For simple or complicated matters, typically monitoring can be sufficient. So this is more of your known knowns. I've seen this problem before. If I experience these symptoms, I have a run book or something that I can follow to go resolve that problem. Whereas for more of the unknown unknowns, you have to more probe and ask different questions and analyze and maybe even react and then figure out like what's happening. That's kind of where observability comes into play. So this is kind of a different mental model, so maybe it's helpful for you. I thought it might be kind of relevant to the topic today. Next, DIY, do it yourself. In this case, it's kind of similar to the build versus buy conversation that was being had in the earlier talks. What do you want to do with the observability information? Like, do you want to build your own solution to actually store it and process it, or do you want to buy a solution? And for each of those, I think there's a couple different dimensions. You have open source projects that you can kind of use off the shelf, or proprietary solutions that you can use. Which one do you choose? Well, I mean, open source, quick, free, kind of easy to get started. Sometimes it becomes more complicated because it's a black box that you may not know how to actually operate it or run it at scale, or maybe you need to hire a team to actually run it kind of long term. Vendors, they kind of offload two aspects. One would be the operation aspects. Sometimes they also offer enterprise features. Sadness. I'm not even doing anything. That's really, really sad. I'll continue talking and hope that it comes back. But the problem with vendors, of course, is the price aspect. So it's not free to use a vendor to run these tools and solutions. So that...
No, you're good. We might try to.
Yeah, I need to. See if it comes back. I don't know. But the questions that you need to answer when you're deciding about how you want to do it yourself is like, where do you want to spend your time? What's the opportunity cost of doing something else? What's your budget for it? And don't say your budget is nothing. Like if your environment's down and you're losing a lot of money, you have a budget to solve some of these problems. But where do you want to invest it? Do you want to hire subject matter experts that run tooling for you inside? Do you want to offload to a vendor that you can then blame if things are not working properly? It's your choice at the end of the day, depending on your business requirements, but some decisions need to be made and you need to look over the entire environment when making those decisions. And then finally, we have OTEL, which is the abbreviation for the word open telemetry. Now, some people might be wondering why it's not called like OT, given it's open telemetry. And the reason is because the precursor to open telemetry was two other projects, Open Tracing and Open Census. And Open Tracing was known as OT, so can't reuse the abbreviation here. So OTEL is the abbreviation for open telemetry. This is an open source, vendor agnostic solution with the goal to provide basically instrumentation and data collection. So think of the things that you're deploying in your environment to generate, emit, and transmit all of the telemetry data that you care about. Now, OpenTelemetry does not actually provide a backend. Instead, it supports a variety of different open source and commercial proprietary backend solutions. And you choose through configuration where you want to send your data. We're going to talk a lot more about this today. You can see a rough reference architecture here on the right-hand side. So I want to drill into OpenTelemetry first, and then I want to kind of show you a demo of how you can actually get started with this yourself. OpenTelemetry has a bunch of different repositories, but there's basically three major components. The foundation to everything in OpenTelemetry is what's known as the specification. This is things where the API, the SDK, the data models, semantic conventions, and the like are all defined. This is meant to be an open standard that supports other open standards. So for example, it will be compatible with open metrics. It'll be compatible with different logging standards that are out there. The idea is it needs to be flexible so that you can plug into a variety of different backends if you want to. Quick question for the audience. How many people have heard of OpenTelemetry? Show of hands. How many people have used OpenTelemetry? How many people are running OpenTelemetry in production? Corey, take a look. There are people. So, now, beyond the specification, what you need is basically an implementation of that specification. That's what OpenTelemetry provides in terms of instrumentation libraries and a collector. So, instrumentation libraries is a language-specific way to generate, emit, and transmit, basically traces, metrics, and logs. And then the collector, think of it like an agent or an aggregator or a gateway service that exists in your environment that can collect, process, and transmit this data back out. You can choose which pieces you want to use. OpenTelemetry provides a reference architecture for all of it. Now, I can't drill into all the specifics in this talk, but I want to talk at a high level the value of, say, an open standard in terms of the OpenTelemetry specification. And I want to do that through some examples. So one of the biggest values that's provided here is data portability. What I mean by this is a couple things. One, there's something known as semantic conventions in OpenTelemetry. Think metadata, think key value pairs, think information attached to your telemetry data. Basically, semantic conventions help normalize what things are, objects, items in your environment. For example, let's say you're calling an HTTP endpoint or you're calling a database. If we can normalize what that looks like across all telemetry, we can do some pretty powerful things. Now, the examples I'm showing here, these are tracing or distributed tracing semantic conventions, and you can see some of the names that OpenTelemetry uses for these different types of objects. But let's say I have an application that I've instrumented with OpenTelemetry, and let's say I'm running in a cloud provider environment and I'm using a cloud provider's database, and my application talks to that database. Now, most monitoring or observability tools, clearly I can collect all of my own application data, but like AWS, GCP, they're not going to give me their telemetry data. They're not going to instrument their apps the same way I'm instrumenting mine. Maybe I can use their tools like CloudWatch or what have you, but I have to stitch that together. OpenTelemetry will allow you to basically do something like inferred services. I can see all of my application telemetry data and all of my calls to, say, the cloud provider database, and I can now visualize that, query over it, and ask questions about it in my observability backend because OpenTelemetry has these semantic conventions, which is very powerful. So as long as the destination of your telemetry data supports the OpenTelemetry standard, you can start to do some of these more powerful things like see in a service map a database that isn't instrumented by you. Now, you don't get full visibility because there may be other things calling that database, but at least for all the things that you control, you now have visibility into that data set. The other quick example I want to give that OpenTelemetry has made a primary concept is this notion of resources. So telemetry data from your applications is great, but where is that item running? Like which cloud provider, which Kubernetes cluster, which pod, what environment? This is called a resource in OpenTelemetry, and all the telemetry data is tacked on with resource information. This allows you to do problem isolation and to get to root cause a lot faster. For example, I might be experiencing an error and getting a lot of error messages coming in, but if I can quickly identify, like in this example, that there's a single pod that is experiencing all of those issues, I've now isolated the problem and I can focus in on that area instead of looking at my entire environment to try to figure out what is going on. As I mentioned before, instrumentation libraries, these are an implementation per language. The idea here is you can install a single thing into your application depending on your language, and you can get all of the telemetry data. You don't need a different instrumentation library for traces or metrics or logs. The goal is to provide a single solution for all. Now, OpenTelemetry prioritized tracing first. That's basically fully supported in all these languages today. Metrics has recently become GA, and many of the, or stable is the term that OpenTelemetry uses, and many of these languages have OpenTelemetry metric support, and then logging support has also been added. There's also talk of adding continuous profiling. In fact, a group recently got together to start defining like what that data model might look like in OpenTelemetry. But beyond your application, you probably also want to understand what is the impact to like users of your system. That's where something like RUM or real user monitoring comes into play, and OpenTelemetry has instrumentation libraries for mobile web browsers and mobile devices like Android and iOS. And then, of course, you have different packaging depending on how you run your workloads. Maybe you're in a serverless environment, and so you need wrappers or layers or extensions, and OpenTelemetry provides this per language. So again, a single solution is the goal where you can get all the telemetry data that you care about. And then there's a collector. This collector is a single binary, and you can choose how you want to deploy it. So if you want to run it as like an agent, let's say I'm on Kubernetes and I want to run it as a daemon set on every single host, you can do that. If you want to run it as a standalone service and you want to have it aggregate information or maybe reduce the information that it's sending, you can do that. Sorry. And the collector is an extensible architecture. So the idea here is it's made up of a few different components. Receivers, how you get data into the collector. This can be push or pull based. For example, it's very common for traces to be sent from the application directly to like an agent or directly to a backend. Whereas metrics, maybe I'm using Prometheus and I'm kind of scraping an endpoint, that would be more of a pull-based mechanism. OpenTelemetry supports both models. Processors are what I want to do with the data after I've received it. Great examples here would be like CRUD metadata operations. CRUD, create, remove, update, delete type operations of the telemetry data that I have collected. And then exporters, just the opposite side of receivers, push or pull based ways of where I want to send that data at the end of the day. Now the collector allows you to, through YAML configuration, to define how you want all of this to happen. They call it a pipeline. And you can see a couple examples on the slide here, like the orange pipeline is receiving in one format and then exporting in a different format. So the collector can actually translate the data. This is why it can support a variety of different open source and commercial backends. Or the green one, where it's receiving in one format and exporting in two different formats. So let's say I want to try two different backends. Maybe I'm going to do a bake-off, or I'm going to switch from one backend to another. You can do that with the collector as well. It's able to kind of handle those different types of use cases. The net result is a reference architecture like this. So let's say you're in a more of a greenfield environment and you want to add observability data and be able to collect this. You could go all in OpenTelemetry, you could add it to your application, you can add the collector and you can send it to the backends of your choice, but that's not a requirement. You can pick whatever pieces you want. Let's say you're using Prometheus metric library today. Continue using it, the collector is able to get that data. Let's say you already have your own agent, but you want to add distributed tracing. You could use the OpenTelemetry library to do that and not have to change your agent infrastructure. So again, flexibility and choice is part of the game here because the OpenTelemetry project understands that every environment's different, every use case is different, and we don't want to have a high amount of friction in order to get started. Maybe it's me touching the table. I don't know. We're going to see. Try again. Please come back. All right, cool. So now we talked a lot about OpenTelemetry. This is basically your side of the environment, like what you are doing to instrument and emit this data. And then you have kind of the back end. From a DIY perspective, it's been very common that both of these are treated as a single unit. Let's say I'm going to use, I don't know, let's use Prometheus as an example. I want Prometheus to be my back end for my metrics. I'm probably going to use the Prometheus client libraries. So it's kind of like a package deal. And this is true for vendor solutions as well. Usually vendors will provide their own instrumentation or agent aspects. OpenTelemetry is trying to break the mode here, saying that you don't have to treat them as the same. And the reason why this is important is because instrumenting and deploying like agents and collectors in environments is a non-trivial amount of work. We saw examples earlier today of actually trying to instrument your app. That takes time. You need people that make the code changes. You need to test that, make sure it's performant. You need to roll it out to production. That's a non-trivial investment. What if you could instrument and collect data once and then move to a configuration model where through configuration changes only, you're able to decide where that data goes, how much data you're sending, when you stop sending that data. It makes it a lot easier for at least your side. Now, you still need to go support like whatever's necessary to persist, query, alert, visualize, and the like. So if you're going to run your own backend, you still need to manage that. But you could also use a vendor for that if you wanted to as well. Again, providing you kind of choice there. So with that, I want to give a demo. And actually, when I put this talk together, this demo environment didn't exist. But luckily, some people in the OpenTelemetry community recently established this new repository called the OpenTelemetry Demo Web Store. And I'm hoping that I'm going to be able to show my terminal, but this display is being a little Interesting. So we'll see how it goes. But basically, this is a microservices polyglot, meaning multiple different programming languages environment that is going to be instrumented with OpenTelemetry. And I'm going to be sending data to a variety of open source projects, Prometheus, Jaeger, Elasticsearch, and the like. So let's try this, and I'll try to go very, very slow. So first, I'm already running this. It's actually a Docker Compose file. I'm just trying to prove this is real. I'm going to do this live. We'll see how it goes. And here is the online web store. So it's an online boutique where you can basically purchase items. And this is a microservices backend, which I'll show you in a minute. So I can click on, I don't know, the sunglasses here. I can add it to my cart. I can navigate to other aspects and choose different items like discount coupons. And this is no different than you interacting online with any sort of website. Now, when I do that, what will end up happening is I will start generating traces. So here's an example of basically the operations that I'm just performing from a back-end perspective. And as you can see, it's complicated, right? The front end has to talk to the product catalog and then the currency and the cart service, the recommendation service, like a lot of interactions are happening. And this is all captured for me automatically in terms of spans, which are then represented as a single transaction or a trace. So if you're familiar with distributed tracing, this is an example of it. And then in here, I have a bunch of metadata. So for example, I mentioned some of the semantic conventions. Here's OpenTelemetry defining HTTP calls. I can see the host and the method and the route. Useful pieces of information in order to ask questions should I have a problem in my environment. Beyond this, I have rich infrastructure information. So in my case, I happen to be running this locally on my laptop, so it's less exciting, but it's on Linux, and here's the host name of my system. But let's say I'm running in a cloud provider or Kubernetes, I would start seeing pod information, region information, anything about the environment that would be kind of useful, and then I can slice and dice my data in order to ask questions about what is happening. I can also add information in different aspects. Like in my application, I can add metadata. From a collector perspective, I can add metadata. For example, I'll show you that I've actually added this Monitorama key value pair directly from the collector. So all data kind of coming in, I'm enriching with additional insights and information. Now, this is all being done through the instrumentation libraries I talked about. There's actually two forms. There's automatic instrumentation and manual. Manual means you go make code level changes to your application. That's a little bit harder because again, I need to actually go edit my code. Automatic means I basically change runtime parameters and I start my app up and I get instrumentation automatically. So bytecode manipulation is another term for this. Automatic's a lot easier. Changing runtime parameters and restarting an app, not nearly as challenging as actually making code level changes. I'll show you both in just a second. Then from a Prometheus perspective, I actually have a collector up. It's scraping a couple endpoints here. I can kind of show you that this data is real. So for example, I can see OpenTelemetry collector telemetry data coming in. I can check the metrics of this. I also have HTTP endpoints for my application that are coming in. So basically, the collector can either push information out, so you can do like a remote write type operation, or the collector can also serve as an endpoint that Prometheus can scrape in order to get the metrics to the Prometheus server itself. I also have an Elastic instance up. I'm using Kibana, and I have log entries coming in here, and you'll be able to see when I show you kind of the demo environment that this is one of the services. It's called the ad service. And again, even the telemetry data I showed you for like the Monitorama tag, it's actually showing up in the logging platform as well. So I can ensure kind of consistency regardless of the tool that I'm using. Okay, with this kind of background, I'm going to try very carefully here to show you demos live of how all of this works. So here we go. This is a microservices app. So every folder here represents a different service, and these services are written in different languages. So for example, if I go to the ad service, this is a Java application. In this Java application, if I go look at the actual code for the app that I'm running, the ad service app here, what we're going to see is traditional like Java code, and it's verbose like Java is. But if I search for OpenTelemetry, you're going to notice that OpenTelemetry does not exist in here. So this is just some software developer put together some code. There's no actual instrumentation in this app whatsoever. It's just an application. But it is currently emitting spans that I can see in Jaeger. I can show that again in just a second. And the question becomes, well, how did that happen? And how that happens is
there's this jar file. It's a Java agent. This is specific to Java, but if I add this jar as a runtime parameter to my application, it will automatically instrument it and automatically have it start emitting spans, metrics, and other useful information. Well, how do I change my runtime parameters? I have this, I'm using Gradle, so I have a build Gradle file, and right here I'm just saying pass the Java agent flag and use the jar file. So pass in the jar, start my Java application. That's pretty much it. The only other thing would be if I care about environmental variables that configure more information about the ad service, and that I can also specify here in my Docker Compose. So I'm saying like, I want to set a service name. I want to call this the ad service. Maybe I don't want to send this to the collector. I want to send it directly to a backend. I could specify an endpoint that I want the destination for that data to exist. That's it. Start the Java application up. I now have telemetry data. Extremely powerful. So it doesn't have to be hard to get started with distributed tracing. Now, if you want to manually instrument it, there are of course more steps. And what I'm showing you is a Java-specific example. It varies a bit depending on the language that you are using. So next, let's take a quick look at the currency service. This is a JavaScript application. What does that process look like? Well, here I created a simple tracing.javascript file, a single file, with basically some boilerplate code for OpenTelemetry, specifying like the dependencies that I want to have and that I wanted to use auto instrumentation. And then I start my JavaScript file here with the tracing.js file. That's it. Again, pretty easy to get distributed tracing and metric information out of my JavaScript application. I'm not really changing the code. I'm basically adding a dependency and I'm adding a runtime parameter. Let's give one final example. We'll go to the email service. This is a Ruby application. And the reason why I want to show this is because it doesn't have to be an either or, like an automatic or a manual. It can also be a both. So for example here, if you're familiar with kind of Ruby code, we have our requiring dependencies. This is similar to kind of the JavaScript or Python or anything else. Then you call in your auto instrumentation libraries. So this is using Sinatra. And then if you want to, you can actually enrich it. So let's say I want to set my own metadata. Here's me adding a bunch of key value pairs specifically in my code. So if I want to enrich what's actually being emitted with the auto instrumentation, I can do that. Let's say I have my own function, like sending email. I can generate my own spans manually. Yes, you have to add it manually if it's not auto-instrumented, but a few lines of code, I have a tracer, I have spans, it's pretty easy. This is kind of similar to adding metrics or custom metrics into your application. You're going to need a few lines of code. It's no different with OpenTelemetry. The idea is you can do this regardless of the signal that you care about. Okay, so then finally what I want to show you is the OpenTelemetry collector config. So as I mentioned, it has receivers. You can kind of see them at the top. I'm using a small subset, but there are tons available. There are processors. So for example, how I'm able to add my operating system information is through this resource detection processor. These exist for cloud providers as well, OpenShift and other environments, Kubernetes and the like. So you can actually enrich all of the telemetry data that's being emitted. You can add your own metadata information. So for example, that deployment.environment that I showed you with the Monitorama value, that's me adding that as a YAML configuration file into the collector, and now all telemetry data that's being processed will have all this information. And then finally, I can define a variety of different pipelines. So for example, for traces, I'm receiving them in OTLP, which is OpenTelemetry's protocol. That's what the instrumentation libraries support by default. And then I'm exporting it in Jaeger format to a Jaeger endpoint. That's how you saw the Jaeger UI. Same for metrics being Prometheus, same for logs being Elasticsearch. I can add as many pipelines as I want. I can change the configuration. All of it's pretty straightforward.
All right, so wrapping up, I have a bunch of resources if you're interested in like trying this stuff out. Many of these projects are CNCF or Cloud Native Compute Foundation projects, which means they are vendor agnostic. Some of these are just open source projects, so there may be a vendor behind them, but they're open source and kind of free to use. But feel free to try out any of these. It's kind of plug and play with OpenTelemetry. And with that, that wraps it up. Thank you so much for attending.
Awesome, great work. Lovely printers and presentations are the two things that we have not yet figured out. So if anyone in here wants to solve some real tech problems, presentations are the way to do it. All right, remember that sponsors are the lifeblood of these events. It's how we can do them. Make sure you spend some time to go and check them all out. We're going to have 3 sponsors up right now to give their spiels. First up is going to be Sumo Logic. Sumo Logic.
How can you resist the dulcet tones of Pete Cheslock? Okay, where did my screen go? It was working. Oops. Am I? Well, we had it working. It thinks it's there. Unplug it and plug it back in. Oh, okay. Yeah, Monitorama thing is still up. Okay, very good. So, I am here today to talk to you about how Sumo Logic loves open source. So, if you're not familiar with many of Sumo Logic's ongoing investments in open source, been actively investing in open source observability for the past several years. This includes their silver sponsorship in the CNCF, longtime sponsors of CNCF, and also active contribution to OpenTelemetry. I was going to have to say a bunch of words about what OpenTelemetry is. I don't have to do that now since you just heard about a half an hour's worth about that. But Sumo is active participants in the OpenTelemetry logging SIG and our OpenTelemetry collector approvers. They acquired Sensu last June. So any Sensu fans in the house, we're now found a new home here at Sumo Logic. And also have just recently open sourced the SLOgen project, and are, of course, I'm speaking now because we are platinum sponsors. Here's some recent announcements about our various different open source initiatives that have been in the news. The one I'll call out here is actually not open source, the one back in February, but sort of demonstrates the open nature even of the Sumo Logic platform, that Open Analytics beta. If you're interested to learn more about that, come visit us at our booth. Moving on. And now my slides are going to freeze. There we go. So open source has always been core to observability data collection at Sumo Logic. So here just demonstrating the stack that makes up the Sumo Logic Kubernetes solution. And rather than try to do a live demo, you can scan this QR code and go see an actual open source data collection in action live demo of that Sumo Logic Kubernetes observability solution. It's quite cool. Back in April, we announced the general availability of the Sumo Logic distribution for OpenTelemetry Collector, I think is the name. It's a little bit of a mouthful. If you, Corey sort of shouted out that there's a lot of talk about OpenTelemetry, but maybe nobody's actually using it. We would like to argue that fact. If you're looking for vendor support for beginning that OpenTelemetry journey, then come talk to us. And moving forward, part of the announcement was we're actively investing in OpenTelemetry, the OpenTelemetry Collector, as the unified observability agent for logs, events, metrics, and trace data for Sumo Logic. And then just last month, we were at the Noble 9 SLO Conf event, where we announced the contribution of SLOgen to the OpenSLO standards project. You can check that out on GitHub at OpenSLO/SLOgen. Now, I'm here to talk about Sensu. So for any of you who know me as the co-founder and CEO of Sensu, you should know by now that we were acquired, as I already said. And I speak on behalf of the entire Sensu team in saying we couldn't have found a better home in terms of partnering with an organization that's so committed to open source. And while we have been busy working on integrating Sensu into Sumo Logic, we're also continuing to develop Sensu as a standalone product, including a huge milestone release for Sensu that introduces an integration marketplace that we're calling the Sensu Integration Catalog. It's an in-app marketplace that enables self-service infrastructure monitoring with a growing collection of turnkey integrations. And one thing that's unique about the Sensu marketplace implementation, besides the fact that it's an open marketplace, is that these integrations aren't just like I want to click on some data I need to collect, and then that's going to instruct me to go out of band of the product, edit some YAML files, restart dozens or hundreds or thousands of agents, but we actually provide that real-time deployment of infrastructure and application monitoring integrations. And that includes user prompts to customize data collection, alerts, incident management, and even automated remediation integrations. You can learn more about the contents of that marketplace. It is an open marketplace and low-code development platform for infrastructure and application monitoring, and includes, was that my creepy Pete time reminder? Thank you very much. Includes the ability to sort of run your own marketplace, so you can clone this repository and customize it to your organization's needs. This is we're not going to actually watch it, hopefully it doesn't make any sound. You can scan this QR code to see a demo and learn more about that marketplace. And finally, if we go to our next slide, come to our booth or to our after party. If this is your first time at Monitorama, there's a very cool thing that happens on Tuesday nights. It's the sort of like sponsor pub crawl, we like to call it. We are hosting an after party along with PagerDuty and Catchpoint. It's a rooftop bar. Who doesn't love rooftop bars? Let us buy you a drink and we can talk about all this stuff. Thank you for being here.
You know, I just want to say shout out to the QR code. That was really the winner of COVID, right? You know, no one ever used QR codes before now. All right, next up, we got VMware. VMware.
What crowd? All right, all the tech work and prep work. Just kidding, it works. All right. Exciting to be here at Monitorama. Welcome everybody. We appreciate the opportunity at VMware to partner with the Monitorama team. My name is Michael Glancy. A few years ago, VMware changed the way we approach compute with virtualization. Likewise, VMware's investment in modern applications, for instance, acquiring Wavefront about 5 years ago, we're now changing the way that we go about modern applications, the way we approach DevSecOps, and specifically observability. Laptop respond. I want to start today by talking about some of the findings we did in a research. We commissioned a report about in our 2022 standard or state of observability report. First thing that is probably could be obvious, maybe not so obvious, but that traditional monitoring breaks when used with modern cloud applications. 7% of the customers reported that these legacy tools, and they're still satisfied, but that's only 7%, where 96% said there are issues with that approach. There are gaps, as you know. Our customers reported this lack of end-to-end insight as a top challenge that slows down incident resolution. Another one is the open source tools that customers deploy are not without cost, and those challenges are much more pronounced within larger organizations. From the research, among the most desired observability capabilities were, one, multi-source data monitoring to do it at scale, to include metrics, histograms, traces, and span logs, and bring it together by correlating customer and business metrics for both application and infrastructure. Notice this growth of respondents from last year to this year increased from 57 to 67% who feel it's a mistake to monitor infrastructure separate from applications. This State of Observability report is available and download from our VM Observability website. VMware Observability, Tanzu Observability, provides tools that unify or provide that full stack observability. We do it at scale with some customers like Intuit and Reddit and Snowflake ingesting millions of metrics per second. We remove those silos where groups rely on their pet projects or their special tools and bring everything together to correlate. And as you know, organizations are trying to increase and adopt multi-cloud strategies with more modern application development and with the requirements becoming or being a modern digital business. And with some of those challenges to manage and modern applications and performance across distributed environments is complex. It's hard. It requires integrated observability, both within the stack and across clouds, that traditional siloed monitor tools cannot provide. VMware Tanzu Observability by Wavefront delivers enterprise-grade observability for multi-cloud and Kubernetes environments, all Kubernetes environments, and it does it, as I mentioned, at scale. This allows our customers to quickly troubleshoot, reduce performance bottlenecks across the infrastructure and applications, and in turn, achieve higher availability of business-critical services to their end users. As a new entrant, and for the first time, VMware Tanzu Observability is a visionary in the Gartner Magic Quadrant for APM and observability. Observability, as you know, is becoming more mainstream, which is why Gartner decided to include it this year in their observability in their APM Magic Quadrant. Besides our stellar customer reviews, we were placed as a visionary because of scalability, support for open source like OpenTelemetry, and an ROI that truly delivers flexibility and choice to our customers. VMware Tanzu Observability, formerly Wavefront, takes a holistic approach to APM with best-in-class multi-cloud observability. In addition to the open source, we also offer hundreds of out-of-the-box integrations. Here are just a few. VMware Observability provides powerful, flexible analytics at an unprecedented scale to ability to adjust millions of metrics or points per second, correlating those data across applications, infrastructure, developer and DevOps tools, and packaged out-of-the-box dashboards, metrics, and alerts. We provide flexible ingestion with support for open source tooling like OpenTelemetry, fast troubleshooting and predictive analytics, leading anomaly indicators and proactive alerts. This recognition by Gartner affirms our commitment to giving customers and organizations like yours the solutions that you need to succeed in your cloud journey. Now, most important though, why are we really here? Yeah, we have a happy hour tomorrow night as well. So please join us tomorrow night. It's only a 6-minute walk away. It'll be at the Independent Sports Bar, 225 Southwest Broadway. Come join us or come by our booth. We have some VMware socks because you got your Monitorama socks, you got your VMware socks. You need to change your socks. We're here 3 days. Please change your socks. We're also having a drawing for, yes, we have the box there, right there. It is the kit. It's not just the box. For a Lego Millennium Falcon set. So please come join us at our booth. Come by for a conversation. Come by for a demonstration. Thank you so much. Have a great week.
All right. And our last sponsor before our next speaker is going to be Big Panda.
Since great speakers are finishing early, I have been tasked to take as much time as possible. So you guys are in safe hands, don't worry. Just kidding. All right, welcome to the session of Too Many Tools, Too Much Noise. My name is Bhushan Zadav and I'm part of the Big Panda team. How many of you in the audience agree with this image? If not, does your IT stack, by the way, look like this? If not, then probably you have achieved nirvana and should head out, enjoy the unique neighborhoods of Portland. But if yes, you're not alone. What's happening here is there is a lot of legacy infrastructure and applications that are provided by monolithic vendors. Today's organization, on top of that, they have built their modern infrastructure and applications. You have monitoring and observability technologies, which again keep on growing, changing, and generate more and more data, or sometimes just pure noise. From an operational standpoint, what's happening is this is getting difficult to manage, right? If you're a DevOps or an SRE engineer, right, and if you are in charge of your own monitoring tool, you know modern incident management can be challenging because of the massive infrastructure, massive environment, tool fragmentation, and so on, right? For DevOps to successfully build and operate, they need full stack visibility into their network, into their multi-cloud environments, right? Believe it or not, the actual health of the application is buried deep into thousands of alerts, their change data, their topology data that's coming in from 15 or so monitoring tools, right? So let's just say if you have a critical outage at hand, a valuable DevOps time is wasted to triage and to resolve those outages, right? The other problem is the CI/CD pipeline. The pace of change has accelerated so dramatically that thousands of changes are being pushed across these various siloed tools, right? It's hard to keep a track of these changes, and any one of those changes can result in an outage. So since velocity is critical to DevOps, it's impractical to assess the risk of each of those changes. And at the same time, like if you are a DevOps and an SRE, you prefer using your own tools because of the certain type of applications. At the same time, you have your standard IT teams or centralized IT teams who wants to standardize everything, right? So there is this constant conflict to preserve tool autonomy. So what does it mean for DevOps and SRE engineers, right? I mean, despite having world-class monitoring and observability technologies, there are still outages, right? You guys are still experiencing performance problems, latency issues, so on and so forth, right? So how do we solve this problem? Like, despite having significant investment in these tools, how do we make sure that DevOps and SREs are getting complete value from their tools? And we believe there is this common abstraction layer that's missing to bring the additional context, and that can simplify the whole incident management, can make it much simpler, right? And this is where I think AI ops in event correlation automation is the answer. I mean, AI ops can mean so many things, don't get me wrong. Like AI ops in observability can mean, doing anomaly detection and so much more. But there is another form of AI ops that we think is needed here. So event correlation and automation is the critical piece that might be missing as of today. What it does is it takes in tsunami of data from layer below, which is your alert data, your change data, your topology data. It not only normalizes it, but it enriches it to bring that additional context, right? It does correlation to detect outages, and at the same time, you're kicking off automation to try to resolve those critical incidents or critical outages, right? So Big Panda was a purpose-built event correlation and automation platform that represents the best of breed solution to solve the urgent and pressing needs of your IT ops teams, your DevOps and SRE teams. So more monitoring is not the solution. Getting more context and meaning out of those existing tools is the key here. So stop by Big Panda to learn about how DevOps and SRE teams can gain full stack visibility, can increase their efficiency and release velocity, and retain tool flexibility. Me and my team would be happy to help you on that. Thank you.
Awesome. Thanks again to all the sponsors. There'll be some more this afternoon. Make sure to get over there, get some socks and shirts and all that good stuff. Let's try this one. So while we're just getting set up with our next speaker, lunch is going to be coming up next after this session. Join the lunch party Slack channel. There's a lot of great information in there, a lot of great lunch spots, food trucks, and etc. If you're not in there and you're registered, send a message to info@Monitorama. Jason will make sure you're in the Slack workspace. And we'll be back here at 2 o'clock for our next talk. So try to get back maybe like 1:30, 1:45. But we will start pretty much sharp at 2 o'clock. So there's definitely plenty of time. Grab some lunch and go from there. Let me just get over. All right, we're not there yet. Not yet. Come on, you can do it, computer. Oh, it may not be the dongle. May not be the dongle. We did try a different dongle. We tried a new one.
It's not me. Is the dongle powered?
I don't know about this one, but let's switch back. And we tested, in true form, we tested this before. It was good. There we go. Mm-hmm. Oh, man. Almost. Try again. I know, we're so close. Maybe. All right, don't breathe on it too much.
Try to do it without taking a breath.
And we're going to full screen that, and let's kick it. All right, let's give a big round of applause for Jonathan.
Hey folks, it's a pleasure to be here. I'd like to talk about some of the lessons we've learned building FlowMill, which is a monitoring solution for network monitoring solutions, now part of Splunk. I'd like to discuss the question, how can we build observability systems that can handle large data volumes efficiently? And I've tried to take the lessons we learned that are more generalizable to the broader community and are not eBPF specific. So if you're building tracing, logging, or metric system, I hope this would be useful to you. I'm going to start by showing you some of the network data that is collected and why we chose eBPF to collect it. Look at some measurements of the volume that eBPF generates and the cost constraints on the system. And this motivated us to build solutions, techniques to handle this large data. And at the heart of these techniques is a domain-specific language that we call render, where developers can specify the schema of their observability system. I'll give more details as we talk about that. I'll then switch gears and move from the collection side to the storage and query side, the database, and go through a retrospective of what we did to scale Prometheus and what was still lacking there. I hope to take a step back and then discuss what would these capabilities of handling large data volumes at scale efficiently could open for our community in terms of use cases. So when you think about building a network monitoring solution, the first thing you think about is let's get measurements of sockets, the communication between components of the system, and we can get information about throughput, packet drops, latency, and such. But socket data is not as useful for users, we found. Users want to have the context of the communication. In this case, maybe the process, the container, and the host that traffic is coming from and terminating into, so both sides of the connection. And even that is frequently not sufficient. You want more context in the form of information about the VPC or the machine from instance metadata, information from Docker and your orchestrator, and information about address translation that is happening to traffic, and a mapping from external addresses down to names that users can identify, maybe from the cloud or DNS. Traditionally, collecting network metrics is done from the network. But unfortunately, by the time that application data hits the network, most of the context is lost. Instead of seeing the process and container, you see IP addresses and ports, and reassembling this context, especially in a microservice environment, is hard for observability systems. Also, collecting from the network has relatively high friction. On-prem, operators need to modify switch configuration to extract telemetry, which is not as easy as just deploying software. And in the cloud, access to detailed network data, it can become very, very expensive. In our community, many observability systems are built around instrumenting applications, for example, tracing, logs, and metrics. And instrumenting applications gets you great application context. But applications don't have ready access to the low-level metrics like packet drops, high network latency, or DNS failures. And also modifying individual applications can impose friction to deployment. In contrast, the operating system sits between applications and the network. So it has visibility both into the application context in the form of process and container, and the low-level networking information. And with eBPF, it is possible to deploy these systems like you deploy software. So that has very low friction. You can instrument every application running on a node and get network information for that without changing individual applications. But eBPF generates a relatively high volume of event data. Here you can see measurement from two different production clusters, one with running containers and one without containers. And you can see that eBPF instrumentation generates between 1,600 and 5,700 messages per node per second. Compared with tracing, network instrumentation can be similar or higher volume, and there are two reasons for that. One, for every span from tracing indicating a cross-service call, there might be multiple throughput, latency, and packet drop messages from eBPF. And secondly, eBPF gets this 100% visibility across every application running in the operating system, including system services and every service interaction, whereas tracing systems frequently have a fraction of coverage. It could be large or small, but this means that eBPF might generate more traffic. Although eBPF generates similar or higher volumes of data compared to tracing, the expectation from users is that you'd be able to run the system at a significantly lower cost. More like collecting metric data, maybe tens or hundreds of metrics per node, but not as expensive as a full tracing system. The saving grace here is that the raw socket data is not as useful for operators to perform root cause analysis, so you don't need to save the raw socket data. So while there's higher volume, you don't need to save all of it, you can save aggregate, so that reduces some of the strain. Overall, the high volume and low cost requirements mean that there is huge pressure on reducing the cost per data point for collection and processing. And there is also smaller but still material pressure on the storage system. So now I want to talk a little bit about collection and processing and some of the techniques we use to reduce that, the cost per data point. When we started building the system, we were hunting for a messaging framework, a library to handle messaging. And we came across this benchmark conducted by the Flat Buffers team. The Flat Buffers team compared several of these messaging frameworks. As you can see, Protocol Buffers Lite, JSON, XML, and Flat Buffers. And they compared these frameworks to encoding with raw structs. Raw structs mean just saving data into memory without special encoding. So that is the ultimate low overhead in encoding and decoding. What they found is that raw structs are more than 15,000 times lower cost to decode than protocol buffers, and that raw structs are over 1,000 times cheaper to encode than protocol buffers lite. Protocol buffers encode messages very efficiently. They do work in order to get very small encodings for fields, but after compression, the savings for protocol buffers compared to compressed raw structs was less than 10%. So you do all this work and the size is not significantly smaller. If you think that the benchmarks are representative of the networking data sets, then think back to the last slides where I showed that eBPF generates between 1,600 and 5,700 messages per second per node. The encoding number means that collectors would need to spend between 30% to 100% of a core on every node of your system. So almost a core for every node of your system just to encode networking-based messages. That is a lot per node. And if you look at the decoding numbers, then decoding all the messages from a 1,000-node cluster would take between 500 and 1,700 cores. Yikes! That is way, way too much as cost just to decode all these messages for a 1,000-node cluster, and it is outside the realm of feasibility for network monitoring. We needed something better. This led us to ask the question, can we get the nice properties that protocol buffers and similar libraries have, like forwards and backwards compatibility and libraries that handle encoding and decoding, and also get the awesome performance that you get from raw structs? This motivated us to build Render, which is a language for specifying the schema of observability systems. The developer writes a file specifying what data the system collects, and a compiler that comes with the Render language compiles a library that handles encoding, decoding, forwards and backwards compatibility, state synchronization. I'll talk about these in the next few slides. For message encoding and decoding, the developer specifies the message fields. This will look familiar to you if you know protocol buffers or Thrift. So developer specifies the fields that the message has, and the compiler generates the struct that holds the message. The compiler also generates functions to encode messages for eBPF and C++. So here's how one of these function calls looks like. It's pretty straightforward. This is an eBPF function. And the compiler also generates these stubs for handler functions in C++. So the developer has to come in and just implement the handler logic, and the framework handles everything else, decoding, dispatching of messages, and so on. Using these structs, we were able to get super cheap encoding and decoding between eBPF code running inside the operating system and the collector process running in user space on the same machine. The eBPF code and the user space process are built together with the same build system, so we can ensure that they use the same version of the protocol, so the same struct, so they're compatible. But if you look at the broader system, you'd want forwards and backwards compatibility. You have, this is how a system is deployed to a Kubernetes cluster. On every node, you have a kernel collector that collects networking data using eBPF. There's also a Kubernetes collector that collects information about deployments, stateful sets, jobs, etc. And an AWS collector, generally a cloud collector, that collects information about network interfaces, for example, the names of RDS instances and elastic load balancers. There is a component called the reducer, which assembles all the data from the collectors, is assembled at the reducer. The reducer fuses it together, takes all the metadata from the metadata collectors and puts it together with the data, aggregates, and pushes out metrics. We wanted all of this communication between the collectors to the reducer to also benefit from the low overhead of encoding and decoding. And one of the reasons protocol buffers and similar frameworks are so popular is because they handle this for users. With struct-based encoding, we had these two structs. So I'll go through an example. On the right-hand side is a struct that maybe the reducer is built with, that it expects. And on the left side is a previous version of the message that maybe a collector was built with. We need a way to translate between the two. Luckily, the render language, when it builds the struct, it also knows how the messages are laid out in memory. So it can produce descriptors. So here's an example of a descriptor. You can see for the left-hand side, version 1 of the message has field 1 in bytes 0 to 3, field number 5 in bytes 5 to 8. I'm doing it from memory because I can't see it very well. Here it is, 4 to 7, and so on. With descriptors for both versions of the messages, for two versions of the message, it is possible to construct what we call a copy table. So instructions to copy the common fields between the versions. In this case, you would copy bytes 0 to 3 in version 1 to bytes 0 to 3 in version 2. So those are field ID number 1. And you'd copy bytes 8 to 11 in version 1 to bytes 4 to 7 in version 2. That's field number 17. Given this copy table, after you have it, processing an individual message is very quick. You just need to run through the copy table and copy some bytes. In this way, we were able to front load a lot of the logic to decode messages to sometimes when the collector connects, and then message processing became much faster. We actually took this to the next step, and we built a component, the transform builder, that takes the copy table, the set of instructions, and instead of running through a system that interprets that copy table to translate between messages, it just in time compiles a translator function to do the translation. In this case, with this copy table, you'd need 2 loads of a word and 2 stores to save it to the destination struct. So this further accelerates individual message handling. Even when we had efficient message encoding and decoding, we had a huge source of cost, which was metadata. In a large production system, we measured that for every container in the system, there were thousands of process and socket messages and hundreds of thousands of socket measurements. This means that if we had encoded container information, container metadata on every socket measurement, we would have repeated the container metadata over and over and over again hundreds of thousands of times. And we would have spent all the CPU cycles and the message size in order to do that. So we wanted to avoid that. What we did was extend the render language so that a developer can specify basically the graph you see on the screen. They would specify that a socket has this and that metadata, and a socket belongs to a process. That a process has this and that metadata, and a process belongs to a container, and so on. The collector sends out these messages saying, here's a new socket with this metadata, here's a new new process with this metadata, here's a new container with the metadata, and also when the sockets, process, or container are closed. And the render compiler generates all of the bookkeeping code to track all the live entities in your system and clean up either when a socket, process, or container are closed or when a collector disconnects. It does all of that for the developer, so that the developer, when it handles a socket measurement, all of the metadata for that socket measurement is already available in the reducer in memory. And you only have to send each piece of metadata once. This also allowed us to build the eBPF instrumentation that was much more modular. If you think about it, if somebody tomorrow wants to build a file I/O collector and not a network collector, they can, instead of implementing the socket entity, they would implement a file descriptor entity, and they could reuse all of the process and container and host logic that we've already built. That means that all of the effort that the community puts into developing these collectors can be reused. It also means that if someone then extends some of this instrumentation, for example, you collect the Linux capabilities, the security context that the process is running under, all of the collectors built with that infrastructure can benefit. So this was a major bonus of building entities. So some of the takeaways from increasing the efficiency of collection systems. We had a language where you specify the schema, and using that language, we were able to use efficient struct-based encoding. We used descriptors so that the system can front-load a lot of the work of parsing messages, so that processing individual messages later can be much quicker as you have a lot of messages of the same type. Just-in-time translator compilation help accelerate that translation even further. And entities allowed us not to repeat metadata over and over and over. This allowed us to build a collection system for network telemetry that uses under 0.25% CPU and less than 1% network overhead in typical deployments, and where the reducer, to do everything it does on a 1,000-node cluster, takes between 20 and 40 cores. So far we discussed collection and processing of data. I'd like to switch gears and move to the storage and querying side of the system. So database with a quick retrospective of how we scaled Prometheus. We started with a single Prometheus instance to scrape all of the reducer data. We found that Prometheus only handles each scrape in a single thread. The reducer produced more data than a single thread of Prometheus could handle, so Prometheus would fall behind. We then partitioned metrics to multiple buffers and offered that as multiple targets for Prometheus to scrape. This allowed Prometheus to utilize more than one thread, to utilize multiple threads to process this data, and got us some more scaling. The next bottleneck we encountered was that Prometheus was falling behind closing blocks. And Prometheus uses a single thread per Prometheus instance to close blocks and write them to disk. And when there is so much telemetry that is flowing into, so many metrics flowing into a Prometheus instance, that single thread doesn't keep up. So if you have a 2-hour block, it takes more than 2 hours to write out the block. And this means the data kept accumulating in memory, accumulating more and more and more until the out-of-memory killer would kill Prometheus. This was kind of a nefarious failure because when Prometheus is spun back up after the kill, it tries to read the logs again and again. So it's a loop that requires manual intervention. We solved this by scaling horizontally, partitioning the targets among multiple Prometheus instances. We used a sufficiently large number of Prometheus instances so that the single thread would be sufficient in order to close blocks. As we scaled horizontally and scheduled these Prometheus pods on different nodes in the cluster, the next bottleneck we encountered was that TCP was not ramping up fast enough. We weren't able to scrape fast enough over the network. So what we did was we wrote the data from the reducer to Kafka and wrote sidecars next to each Prometheus instance that stream the metric data from Kafka and make it available for Prometheus to scrape. This was our solution. This setup worked, but it had other issues. First, disaster recovery is not a first-class citizen with Prometheus, so we had to kind of build our own. We used Thanos and a handful of home-baked scripts. This setup doesn't have any replication, so whenever you upgrade Prometheus or have any kind of blip in the system, there's unavailability of data. We had to manually load balance the partitions and to avoid hot partitions and all the pain that entailed. But maybe the most painful issue was this loop. If one instance became overloaded and the thread closing the blocks became the bottleneck. So, okay, this was the database part. Why should we care about scaling database and scaling collection beyond eBPF and network monitoring? Common workflow for observability starts with an alert, which is then followed by these cycles of investigation and mitigation. And you end up with the sequence of mitigations that hopefully stabilize the system as you uncover more symptoms of the problem. The day after you stabilize the system, hopefully developers and engineers go back to and investigate some more and find the root cause of the bug, missing safety mechanisms, or missing process. And the more detailed the data set that the observability system offers users, the easier it becomes to investigate a broader set of failures and not resort to moving outside the observability system in order to get that data. So let me go through some examples with network monitoring. With the node data set, a user can find if there's one node in the system with degraded networking. So maybe a hypervisor failure causes that instance to have dramatically lower throughput than other nodes. With pod granularity, it is possible to find failures where a handful of your pods are allocated next to noisy neighbors, offering a lot of network load onto the node networking systems. And so those pods allocated next to noisy neighbors might have worse P95 latency. So that node data set would not be sufficient. You need the pod data set, pod granularity information. With even more information about individual API calls, it's possible to find things like an important service was configured to try to reach out to an on-prem replica of a service and not the cloud replica of a service, and it didn't have permissions to access the on-prem data center. And so that results in a lot of timeouts. You can fix that. And if you compare this to tracing, taking a step back, tracing also, distributed tracing traditionally has this API call boundary detail. But imagine if you could instrument more. What if every function call that a service makes was observable? Not just the cross API boundaries, but every function call. Taking it a step further, what if every if statement that your service executes was observable? Or, to the extreme, if every code line that your service executed was observable. How much easier would it be with increased detail levels for developers to hunt down bugs and performance degradations without leaving the observability systems, without trying to trigger these complex failure modes on their laptops or in small development or staging environments? This could dramatically improve how engineers approach these problems and failures and how they fix and maintain their code. With the experience we've had with the eBPF collector and the reducer, I have confidence that building collection systems for these more intensive data sets is viable. We will be able as a community, I believe, to build these very intensive collection systems with low overhead, low cost per data point. What I think is missing and we should consider solving are databases that are able to handle this data. We need databases that can handle 100 times more data volume at similar cost to what they run today. So in other words, 100 times more data points at 100 times less cost per data point. And I think opening up the more intensive data sets is something that, as a community, we should try to look forward to, and we should try to tackle this database problem. With that, I'm happy to take questions, if there's time. Do we have time? Yeah, we have time. I know this is a lot. And it's before lunch, but I'm here.
All right, we got a question. All right. I was worried about that. Everyone just wanted to eat lunch.
In this slide just here, do you, how much of that 100x scale at same cost do you think is achievable based on current storage prices? Or does storage have to significantly shift as well? Is it as much cost in the database or in the storage layer?
So I'll repeat the question. I'll paraphrase, sorry. So can storage, the current state of storage costs support the more intensive use cases at lower cost, right? Are we, as far as I understand, are we bounded by storage costs? I think we're not yet quite bounded by the actual storage because we have recourse in cheaper levels of storage that is less accessible. So personally, I think that if we build systems that can tier storage to the right cost of storage, so between kind of more of your distributed block, local network-based block storage, NVMe, RAM, and systems like S3 and GCS. Between those, I think there is cost savings to be had. I think a lot of systems today pay for the higher cost, higher levels of service storage for a lot of storage that they don't have to. And so we're not bounded by hardware yet. Great question, thank you. Another question over there.
any challenges scaling the reducer to 1,000 nodes?
Was the question, did we have any trouble scaling the reducer to 1,000 nodes? Yes, of course. This was very fun to work on. So how do you scale one system that is able to process that much telemetry? The threading model, by the way, we are open sourcing this as part of OpenTelemetry. It's in the process of being contributed. To be able to handle this telemetry, we had this threading model where there was no locking between threads. We added in-memory queues, these rings, the ring buffers between different cores of the system, and we had a pipeline where each pipeline might have 10 or 15 or 20 cores. We have 3 stages of the pipeline, one for ingest, one for matching, so getting the 2 flows of every side of the socket together and adding metadata from Kubernetes and AWS, and then another stage of the pipeline for aggregation. And we used in-memory queues between them. Every thread can do bulk work. So you read a bulk of memory from the in-memory queues, you do a bunch of processing on this data, and you move on. Maybe sending some messages downstream to the pipeline. And that architecture enabled us to scale the system quite a bit. So to handle multiple, tens of millions of messages, some of them generated internally between components of the pipeline per second on a single node.
Awesome. Any other questions? Great. All right, well, I hope one more round of applause here. We're going to be coming back at 2 o'clock. If you are looking for lunch ideas, lunch party in Slack. But otherwise, we'll see you all back here at 2 p.m. Thank you. lunch. Everyone ready for a nap? So if you have found like a really good kind of hidden gem lunch spot, drop it into lunch party, let the other attendees know. There's been a lot of change in Portland over the last few years, so places that were kind of always there are sadly not there anymore, and hopefully some new places have popped up. So before I introduce our next speaker, we've got a few of our sponsors will be talking after this before some other speakers. So Fire Hydrant and Lightstep and Influx Data will be doing their presentation after. Again, make sure you have some time to check out the sponsors. They do help this event happen. All right. That being said, now that we're all back and full of food and ready to go, I'm going to introduce Leon.
Thank you. All right, before I start the actual talk, I want to thank all of the organizers of Monitorama. Like a lot of you, I am a first-timer here. This is my first time being part of it, and it's been a dream of mine for 5 or 6 years to have a chance just to be part of this, and being invited on the stage to share some of my ideas is just, I'm just incredibly grateful. So,
Sorry, the mic. Yes.
Oh, over here. Here we go. So again, thank you to everyone who also keeps me in front of the mic. All right, so I want to start with a story. And like all good stories, you have to start with once upon a time. But this is a true story. In 2001, as part of an effort to build a global monitoring solution for Nestle, they agreed to move my family to Switzerland. And that's what we did, which was really lucky for me. We were in the French-speaking part of the country. And that was good because I'd grown up speaking French with my grandmother, and I took French in high school. It was less lucky for my wife, who was born in Spain and has 2 brothers adopted from Colombia, and had exactly 2 weeks of Berlitz French before we landed in country. I didn't realize exactly how unlucky it was going to be, though, until a couple of weeks after we got there, she wanted to meet me for lunch. And so she's driving out, and I get a call from the car, and she said, I think I missed the exit. What was it called again? And I said, oh, it's, well, where we go? There we go, okay. It's Sheb. Oh, okay, it's easy, right? She misses the exit 2 more times. And it isn't until the 3rd call, where she's getting progressively more frustrated about the situation, that it finally dawned on me what had happened. Now, before I tell you about that, I want to point out that all languages have rules and exceptions. Now, Spanish has rules and exceptions. French has rules and exceptions. And it hadn't dawned on me until that moment that my Spanish-speaking wife might not be working under the right context to see a sign that I said was Sheb that looked like that. C-H-E-X-B-R-E-S, Chebre. Just like it sounds, right? It was in that moment that I really learned a lot about technical empathy. I learned an important lesson about putting myself literally in the driver's seat as the user, and if I didn't do that, it was going to lead to some really bad design decisions as well as a really uncomfortable lunch with my wife. So I want to sort of talk about that. Before I dive into it, though, my name is Leon Adato. I am a middle-aged white man on a stage giving a conference talk. This picture should inspire confidence that I know what the hell I'm talking about. More important than that is that this is an oyster talk. I have the parenting educator, Barbara Colaroso, to thank for that idea. What I mean by that is that in 30 minutes, I really can't do a lot to teach you much. In fact, in that amount of time, all I can do is irritate you. Now, an oyster, when it becomes irritated, does one of 2 things. It creates a pearl, or it dies. Now, it is my desperate hope that I don't irritate you to death, but the choice does remain yours if you choose that. However, what I hope is that I give you just the grain of an idea that you will then begin to think about and mull over and layer with your own ideas until you have something that is polished and personal and unique and valuable. So that's my hope. I discovered that day in Switzerland that no matter how simple the interface seems to the developer, if regular folks can't use it, they can't navigate it, you have a problem. And that lesson counts whether you're talking about something as simple as an elevator, I don't know which button to push to get where I'm going, or operating systems. Yes, this is an operating system. It's Microsoft Bob, right? Some of you remember that. It lasted 35 seconds. It was a nightmare. It's also bad for things like cars. This is the 1972 Maserati Boomerang. It is utterly undrivable. Or the roads you drive those cars on. Anyone from San Francisco? This is the 101 turning onto Van Ness, right? Or furniture. I don't know. There was a design meeting where a designer said, I know this is going to solve all of our users' problems. This is what they want. I can't even with this. But mostly it was operating systems. This is also from Microsoft Bob. And the thing that amazes me about this is that this predates Clippy by a lot. And yet they still created Clippy. Okay, the point isn't that these things are ugly. They are. Or that they're unusable, whatever. But an engineer really thought they addressed a problem a user was actually having. And that's not, it leaves users frustrated or confused or horrified. Now, the problem with talking about empathy is that it gets a bad rap as being really touchy-feely. It offends our IT practitioner Vulcan sensibilities. And, you know, the dictionary definition doesn't do anything to really help us about that. In truth, empathy is different than sympathy. See, sympathy is feeling the same thing someone else is feeling and agreeing with that feeling, whereas empathy is the ability to see things from another person's point of view. A person may feel sympathy, but they share empathy. And that's what I'm talking about today. In tech, however, sometimes we get both sympathy and empathy spectacularly wrong. We ask feeling questions about completely technical decisions that have nothing to do with feelings, or we clumsily try to apply empathy and end up sounding awkward or worse, right? And yes, I've heard these things in actual meetings from actual other humans. Anyway, technical empathy, when I say that, what I mean is the ability to see a proposed technical choice from someone else's perspective in order to identify gaps that are in the user experience or the flow or the result. That's what we're trying to do. So let's get to it. I want to start with accessibility because that's what we all should literally be doing every day. You should be starting with accessibility. It should be the first part of our design choices. I will accept a close second to security, but that's it. Really, it's not an afterthought. It's not supposed to be something that we tack on at the end. Accessibility is the first thing that we do. And what I mean by that, I have a few ideas here. Now, I'm not going to belabor the point of accessibility because it is an entire 3-day talk in and of itself. I'm not an expert, and I only have 30 minutes. However, at the bare minimum, everything that is on a screen should be able to be communicated by a screen reader. Every image needs to have alt text associated with it. Every video needs to have closed captions. Everything that uses a color to indicate state needs to have a colorblind equivalent. And to the best of your ability and the limit of your budget, you need to use language localization within your application. That is the bare minimum. That isn't good enough. That's the least you can do. And I'll tell you that if your sphincter is clenching up right now thinking about how hard that's going to be or how much pushback you're going to get, then that's the problem you need to solve. Not the accessibility part, that. And if you're also thinking that you're going to go back to the office and somebody there is going to say, well, I don't know, there's just not enough demand. Fuck you, there is. Those are the numbers. I'm not going to read them all off to you. But there's a lot, okay? And more than that is that every one of us is going to experience one or more disabilities within our lifetime. To design something assuming that disability doesn't exist is the height of hubris. 15% of the world operates with disabilities. Not only that, the last bullet point actually is a nice counterpoint, right? That 1.35 billion people speak English. Only 1.35 billion people speak English. The other part of the 7 million on the planet speak something else, and only 360 million speak English as their first language. So if your application only works in English, you are leaving out a huge population of potential users. So just something to think about. And really what we're getting to here is the next part, which is assumptions. Now, it is one thing to assume that the people using my accounting software know how to do accounting. Like that's safe, that's fair. It's another thing to assume that the person using my accounting software sees the way I do, processes information the way I do, or speaks the language that I do. That's just not okay. That's not an okay assumption to make. But there's more than that. We are human. We have a lot of cognitive biases. We do a lot of these, and we do them a lot. So we need to become, familiar with these. Hat tip to yourbias.is, in case you want this poster. I have it hanging in my office also as a reminder. But second of all, we are developers and coders and IT practitioners, people who create solutions. And so we have a whole host of other biases that just go beyond all of these. If you Google falsehoods programmers believe, you could spend a good solid 2 or 3 days in the Google hole trying to just get through all of them. For example, we make assumptions about names. The null family and the test family exist. There are thousands of them. They exist to do nothing more than bork your database all the time. I don't know which part Peter Vandermeer is going to put in the middle name part, but it's not his middle name. And that last line, that's my name. And the best part of it is the part on the left is my last name. So I'm not exactly sure what you want out of me. If you have a field, if a form field that asks for first name and last name, what do I do there, right? As developers, we make assumptions about names that are simply patently not true across the bulk of the world. We make assumptions about time. My favorite is the first one. In Samoa 2011, Thursday the 29th was followed immediately by Saturday the 31st. There was no 30th. It didn't happen, all right? But on top of that, ask your Unix system administrator about leap seconds. They're delightful. This is why he drinks. It's really, so we make assumptions that time follows in an orderly manner. It does not. And of course, the whole international time zone, like who was drunk enough to draw that? What did they, I don't know. We make assumptions about addresses should be easy, right? Like I just want to deliver a package. No, your mail carrier drinks a lot, and this is why. Because there are buildings that have negative numbers. Can your system handle that? I know I personally as a human can't handle that. Also, apartment 1 is in the same building as apartment 001. They're on different floors. And there are parts of the world where that last address, that is the town of Gondal, right? Like, okay. But also, if that's where I live, I don't know how to fill out your form. I don't know what to do so that the package gets to me. But it goes beyond that. It goes beyond tech. If I know it, and I'm not smart, it must be simple and everyone must know it. How many of you have made that assumption before? Right? We all do that, and that is patently not true, which leads to the one lower down on the list, which is that everybody understands our personal company jargon, or the terms we use for things, or the industry standard words we use in a completely different way, like observability, or whatever, or monitoring, or whatever you're doing, right? So it's not that simple. That we can learn everything we need to know simply by looking at the data. We don't need to talk to those users. No. So we make these kinds of assumptions, and these are actually more pernicious than the technical ones. The technical ones we can solve using libraries or whatever, but this stuff, if you're operating under these, you've got a major problem, and that's my point, is that you cannot address an assumption if you don't know you're making it. So we need to sit down and really think about what our biases are, what our assumptions are, so that we can then learn to get past them. So how do you get past them? Well, it really has to do with asking questions. Nobel Prize-winning physicist Isidore Isaac Rabi said, "My mother made me a scientist." You see, at the time in the 1950s, every other Jewish mother in Brooklyn would say, "So, no, did you learn anything today?" But not my mother. No, she'd say, "Izzy, did you ask a good question today?" And that difference, asking good questions, is what made me a scientist. And we need to be scientists. We need to be good scientists. We need to ask good questions, the right questions. We need to be comfortable asking the questions at all of the people who can answer them. Now, disclaimer, a lot of what I'm about to share with you is not only my own discoveries. I have been privileged to work with some incredible UX researchers and designers throughout my years, and so I asked them for their insights, and this is some stuff that they shared with me. And so I just want to pass it along to you. For example, they shared with me how to run a UX call in and of itself, and that stuff is really small. It's an eye exam, and I did that on purpose because the only one that actually matters is the one in the middle there. You know nothing. I don't care if you wrote every line of code. I don't care if you custom crafted the database with a magnet personally engraving the bits onto the platter. Like, it doesn't matter. You know nothing. You are not the expert because you're not the user. That's the only person who knows anything about how your application should work. And that's a hard thing for us to get over. So when you're running a call, how do you do that? Well, the first thing is to understand the concept of a Johari window and recognize that a lot of us spend a lot of our time validating the upper left corner. Is what I think true, true? And because we spend our time doing that, we end up asking the wrong questions or asking the right questions in the wrong way, when we should be asking in a way that helps drive down to the lower right side, right? We want to know the things that we don't know we don't know. Sort of like the unknown unknowns in observability, but it's for design. If everything that you discover fits in the upper left quadrant, you're asking the wrong questions. So how do you do that? So technical empathy means giving the user space to express their experience, not to validate yours. And this is really interesting. I mean, when you look at the questions on the left side of the screen, they're not bad, right? Is that helpful? Like, what's wrong with is that helpful? You're boxing the user into saying yes or no and then having to defend it, and people don't want to do that. So, but asking, how do you use that today has no emotional weight to it. They don't feel like they owe you a particular kind of answer when you ask them that way. How is that working for you today? Now, they could say, like shit, okay? But they probably won't. They'll probably say, well, but you're going to discover some stuff that you probably didn't know. How do you feel about what you just did? Okay, that's a feely question, right? But in the context of saying, I'd like you to go through and do X and Y and Z, now how did you feel about that? Well, it was really difficult. It didn't feel smooth. It didn't feel natural. Why? Tell me more about that. But the last line is my favorite. And I've done a lot of UX sessions over the years, and you're sitting there looking at a wireframe, right? And you get to a point where you say, okay, so that button over there, honestly, I have no idea what that's supposed to do. And there's a pause, and you know it's coming. Well, what do you think it should do? How do you think it ought to work? And now we're off to the races. If you get somebody on a call who says, I have no idea what it's going to do, and then you ask them, you give them permission to tell you what it should do, that's gold, right there. As devs, as developers and IT practitioners and people who create solutions in general, we tend to focus on the how. And that's fine. I mean, that is our job. How am I going to make this work? How am I going to solve this problem? How am I going to create something that scales? All of those. The problem is that we tend to rope the user into the how. Well, how would you like me to do that? That's not their problem. Instead, we should be asking questions that allow them a chance to give us the what they want to do, but more importantly, why do they want to do it? Why do they think this is something that needs to be done? That's, again, where the valuable information is. UX sessions are best when they uncover how users do their work. Understand the nuance there. Not how they use your tool, how they do their work. And if you're lucky, they will also describe why they do or don't use your solution to do their work. That's really what a UX session is there for, is to find out the work they're doing, because then you can create a solution that helps them do their work. Okay, one other thing, separate from asking questions and stuff like that. If you do not have a place like this, I don't care if it's in the application or the tool or the whatever, or if it's in a forum or a website that's separate, I don't care. But if you do not have a place where people can go and place a request, I want your solution to do X, Y, Z. They can go in anonymously and do it, or they can go in signed up and do it. And also, other users can come by and see that request and then upvote it or downvote it or comment on it. Yes, I 100% agree it should do this thing, but also it needs to show the information in this way, or I need this other information also. If you do not have something like that, then you are missing a rich source of valuable insight. And then once you have something like this, your developers need to go in, and every time they're going to work on something else, they have to justify why they did not pick the item that's been open since 2012 and has 967 upvotes to it. Just tell me why you're not doing that one. There might be a good reason. I'm not saying that you have to be a slave to the feature request list, but I'm saying that developers need to make a conscious choice why they wouldn't do what the users are actually asking us to do. Why would you not satisfy that? So please, if you don't have one of these, figure out how you're going to build one of them. Okay, so mostly unnecessary summary. One of the UX researchers that I know, Joseph Breitreiter, said to me just the other day, he said, I'm constantly correcting engineers who say, we have to do it like this because users are stupid. Okay, users are not stupid. They really don't care about your application. As it says there, it is UI number 37 in the list of UIs they deal with on a daily basis. They just want to be able to get in, get their job done, and get out. And if you make it hard, they won't get in and do their job. They'll find somewhere else to do it. They are working in a situation of high cognitive load. They're solving their own problems. They're doing their job. And that takes up 95% of their brain power. You get 5% of their brain whether you like it or not. And if you make it too hard, you won't get any percent. So really what it comes down to is getting out of the user's way so they can do what they want to do, because like us, they are tired and they want to go home and they just want to do the thing they're there to do. That's what technical empathy is all about. And again, you have to assume that the user is the expert in what the user needs to do, and that we know absolutely nothing. And the only time we break that assumption is in the case when it will build a rapport that invites the user to give us more information and more insight into what it is that they are trying to accomplish. Thank you so very much for taking the time with me today. I am ready for your questions. I got some extra time, so really, let me have it. Yeah?
So what would you say is the most important? Like you said, there's all sorts of features that could be done. If you want to take an application that's not following these concepts of making things a lot better, what would you say is the most valuable thing to start with?
Okay, so to repeat, just in case the sound isn't traveling, what do I think is the most important place to start? If you have an application where this stuff is all not happening, what's the most important thing? So again, I think accessibility has to be the first thing. First of all, you'll discover a crap ton about your application just by trying to make it accessible and finding out why it can't be or what's in the way. But second of all, if you're not having these user conversations, if you're not able to have these conversations with users, if there's no mechanism by which to interact with users, that is a huge discovery. It is an anti-pattern, obviously. And that's the next thing. Once you do those two things, once you start those two projects, probably everything else is going to sort of domino its way along. You know, you will have that communication channel with users. And you'll have, then you can tweak and tune, and I mean, it's IT, it's iterative, right? We'll make mistakes, we'll learn from the mistakes, we'll go back and we'll do it better the next time. Any other questions? Okay. Well then, thank you very much. Thank you again.
I wasn't keeping track, but if it wasn't the first F-bomb, it was definitely the most passionate, so it was quite good. Awesome, thanks again.
No problem. Do you want me to plug it here?
Yeah, you can take that.
Okay.
All right, so we've got 3 sponsors that'll come out and give you their little spiel, and then we've got some more speakers after that. So The next sponsor that's going to come up and talk is Fire Hydrant. Fire Hydrant! Woo!
Hey everybody, my name is Ryan McDonald. I'm from Fire Hydrant. I'm a recovering incident commander. And
my name is Michelle, and I'm the integrations product manager at Fire Hydrant. And I actually, prior to this, was a product manager for observability at various places for 5 years. And I just wanted to say this is hands down my favorite conference. This is my third Monitorama that I've attended, and I really appreciate the quality of the talks and the organization. And I always come away learning something.
yeah, and we just wanted to let you all know we have a booth out front. If you want to come chat about our product, that's awesome. You want to come talk about incident management writ large, please feel free.
Or observability.
Or observability.
Or outdoors.
Or outdoors. But yeah, super excited to be here with y'all, and thank you so much for your time.
All right, short and sweet, just like your next incident hopefully is. We've now got Influx Data, makers of InfluxDB, up next.
Hello. Nice meeting everybody. Thanks for letting me speak to you. My name is Chris, and I work at Influx Data, and we are the maintainers of InfluxDB. And you might know us for our really fancy socks that we have out in the hall, so come by and see us. But we are also known for our time series database, which is open source, written in Go. So it's a really good excuse for you to learn Go. You can tell your boss that that's something that you need to spend your time on. Or you can also just use InfluxDB for a number of really cool use cases. So we have 2 projects. We have InfluxDB, which is the database. We also have a project called Telegraph. And Telegraph is basically a collector agent. And we have about 300 different plugins, so you can pull metrics from your infrastructure, your web servers, other databases. It supports all kinds of different protocols like MQTT, Modbus, SNMP, etc. And you can use that to pull these metrics. You can actually process the data. You can also do some math on the data, transform that data before you put it into InfluxDB. But because it is open source, you can actually put it into a lot of other data stores. So if you have other data stores, that's cool with us. You could actually put it into some of the databases that are time series or monitoring solutions, that you might see here, like New Relic or Datadog. So super open source. We really like making sure that it's open for everyone. Some of the popular use cases will be, of course, monitoring. So if you're an SRE or sysadmin, all the kind of usual monitoring that you do, you can use InfluxDB and Telegraph to do that. But we also have a lot of developers that are building all kinds of really interesting tools that allow you to monitor IoT sensors. We have customers that are monitoring things like thermostats, like with Google Nest, or the Tesla Powerwall. We also, for some reason, have a lot of vendors that are monitoring rockets and satellites. So in any event, it's a lot of fun, and we all have a ton of really cool things to monitor at home. So even if you don't want to use it at work, check it out at home, monitor your pool, monitor your sprinklers, and just try it. And thanks so much for letting me speak.
Awesome, thank you. And I know you love monitoring so much, I've got one more monitoring company for you to talk with, Lightstep. Lightstep.
All right, now for something completely different. Some people's employers spend however much a sponsorship costs in order to, have them actually talk about their product, but no, we choose a different way here. My slides are not working. Technology. Oh, it's not plugged in. Oh.
Really knocking it out of the park here.
Was it Corey? Someone was talking about the problems of presentations earlier. Okay. There we go. I just need to get the present. All right, you're going to see it in reverse. Hi, I'm Austin Parker, and I head developer relations at a company called Lightstep. You might have heard of our glorious corporate acquirers, ServiceNow. They're great. I love them. No, really, they're good people to work for. So that's not a bit. Everyone thinks that's a bit. Okay. You might have seen me around the internet as the guy that ran the DevOps conference at Animal Crossing. No? Hey, coming back through the September. Sign up today. I also wrote a book on distributed tracing, and I'm a maintainer on the Open Telemetry project, which Corey so gratefully buried this morning. He's officially off my Christmas card list. So I want to tell you about something in the few minutes I have that's really been bugging me for a while, and this is probably going to make me some friends and some enemies, but it's that we have, as an industry, have spent millions of dollars defining observability down into absolute meaninglessness. We have spent so much money on engineering, on marketing, on pushing, sort of the state of the art, but the state of the art really hasn't changed, both in commercial and in open source tooling in a lot of ways. If you're a developer of a commercial open source tool, or a commercial observability or monitoring tool, what you've seen is this relentless expansion of SKUs and new features to meet new buyer needs and desires for expanded platforms. If you're a user, then what you've seen is that endless expansion of features and SKUs for platforms, but not a ton of innovation, right? If you're a developer, you're an SRE team, you're struggling with immature SDKs, you're struggling with poor integration between tools, and honestly, the bigger problem is you're struggling with an ever-increasing system complexity of the stuff you're trying to monitor in the first place that no one is rising to the challenge of meeting. If observability is this simple, right? If it is unknown unknowns, then why does it feel so hard and unachievable? I believe, that a modern cloud-native system needs a modern definition of observability. It needs something that isn't quite so caught up in splashy sales promises and marketing. It should be aspirational but achievable, universal but somewhat tailored. We need a North Star for the industry, for our teams, and for our observability practice that moves beyond traditional thinking about queries and dashboards. And crucially, I shouldn't stand up here and dictate that to you. Nor should I sit on top of my 1,800 Twitter followers and say that I have figured out the life, universe, and everything. 42. But it should be built in collaboration with practitioners, with end users, with developers, people that are working hard to solve these problems at all parts of the industry. So what does that model look like? What does it mean that we need? We need to figure out three things. One is we need guidelines. We need to know what's the separation of concerns between telemetry data, between how that data is stored, persisted, and what are the workflows that get built on top of that persisted data. And that needs to be more than just, here's a really cool time series database, and here's a really cool OLAP DB, and here's a really cool indexable search thing. We also have to think about cost controls. We have to think about data senescence. We have to think about GDPR. We have to think about what happens when the Christian fascists take over the country. We have to think about a lot more stuff with our data than we used to, and observability data is part of that. The second thing we have to think about is primitives. So we all know time series. We all know big number. We know area chart. But we need something different to really tackle these observability questions. We need intuitive abstractions over data that reflect system state and reflect the complexity of modern performance, right? It's not about safety one thinking where you've got, I want to reduce my errors to 0. That's impossible. You'll never have 0 errors. We have to accept that. We have to understand that. Ask Alex Hidalgo what he thinks about that. I think he's up next. The third thing we need are opinionated and intuitive workflows about that observability data and how we can actually, provide value, right? Not just for us, but for our entire organization. This is how I have decided to tackle this problem. I have written a draft of my ideas, opinions, based on what I've known from my years in the industry. Also, I've talked to some customers and some friends and other people about. You can go to this GitHub URL, and we want your feedback. We want your opinions. We want your real-world stories about where you're using observability, where the current models falter, and where you think we can find new answers and new truth. That's why I'm introducing this here. That's why I'm taking my 5 minutes to say, hey, everyone at Monitorama, please go check this out. Give it a star. Give it a, share it with your friends, and let's build the next great vision of what observability can be together. Thank you for your time.
Awesome, thank you. We got our next speaker coming up shortly. So, is anyone here a big musical theater fan? How many? Show of hands. I know a bunch of people backstage, obviously. So if you didn't know, Rent is here. There are signs up. You can actually get tickets. I just looked. There are tickets still available. And my one Rent joke is that I feel like there's a Venn diagram of operators, system administrators who know how many minutes there are in a year, and also Rent fans. There we go. I know there's going to be a couple laughs. There's the famous song is how many minutes are in a year. So anyway, bring it out, Alex. Quick, I'm fading fast.
All right, you do that. Hey y'all, it's so good to be back at conferences where like I have to do all this. I gotta plug things in, I gotta think about what equipment I brought, whether or not I have a clicker. I realized that in the last few years, I upgraded to a laptop that only has USB-C. My clicker's only USB-A. So last night, I had to talk to people on the speakers channel. Sorry, there's a private speakers channel on the Slack.
You weren't supposed to tell them.
About whether or not anyone had a USB hub I could use to even plug in my clicker in the first place. But the point is, this is actually all really awesome to me, because I've missed this a lot. All right, I think we're good to go.
Round of applause for Alex. Yeah!
All right, hey everyone, just want to reiterate, again, it is so amazing to be back up on the stage and to see people, and virtual conferences have turned out to be incredibly accessible and I think very important for many people, and I hope that we continue to learn lessons from them, and I hope that we continue to use them in the best possible way, but also, dear God, have I missed this. The last time I was able to give a talk in person was actually right here in Portland for Lisa, the very last Lisa conference, Lisa 2019 in early November. So it's been 2.5 years, and it's so wonderful to see so many of your faces, and it's so great to be back here again. So I do want to give a quick content warning. We're going to be talking about various different transportation accidents during this talk. I won't go into any gory details, but there will be pictures or wrecks. We will be talking about numbers in terms of potentially deceased people and injured people, and just wanted to lay that out ahead of time. If you want to leave or log off right now, I will not be offended in the least. So I want to start this off by talking about the DC Metro system. So the DC Metro system is actually pretty cool. At 117 miles of total track length, and in fact, in a few months, they're supposed to open some new tracks that will put this at 131 miles. It's the second largest, or the second longest system in the entire US, outside of only New York City. At 91 total stations, it's the third largest, behind only Chicago and New York. And at 57 million yearly riders, it's at the 5th busiest total light rail system we have in this country. And the other thing that's really interesting about the DC Metro, to me at least, is that it's fairly new. A lot of the light rail systems that we have today that we think of as large, such as New York and Chicago and Boston, they were all started a century or more ago. But the very first segment of DC Metro track that opened was on March 27th in 1976, when 4 stations on the Red Line opened. And then about 15 months later, the Blue Line opened, and the first kind of, cohesive idea of a real transportation system really kind of emerged. And then in between 1977 and 1991, the orange, yellow, and green lines opened, and it really kind of became a full-fledged transportation system. And again, I think it's kind of interesting. That's only about 30 years ago that really kind of hit that point. And then on July 26th of 2014, the Silver Line opened. And the Silver Line to me is really interesting because I spent my middle and high school years, my teenage years, living in Northern Virginia. I live in Sterling, Virginia, and the Silver Line, as of 2014, extends all the way to Reston, Virginia, which is right next door. And this would have been so useful to me as a high schooler, living 30, 40 miles outside of DC city proper, to be able to jump on this and head into Georgetown to go shopping, or downtown DC to see a show, something like that. And actually scheduled for this fall, in just the next few months, the next 3 stops, extending another 12 miles. Which will go all the way out to Ashburn, Virginia, for anyone who knows that area. But there's another date in DC Metro history that is very infamous, and that would be June 22nd of 2009. That's when the Fort Totten crash happened. And 8 passengers lost their lives. The train operator of train 112 was also deceased, and 80 people were injured bad enough they had to go to the hospital. Countless others were injured but felt okay to go home. So my name is Alex Hidalgo. For those of you who have not yet met, I'm the Principal Reliability Advocate at Noble 9. And regardless of what my title is today, I consider myself an SRE through and through. I spent 7 years at Google, 7 years at Squarespace, and am now at Noble 9. And keeping things reliable is truly my passion at this point. Now, I want to talk to you today about meaningful measurements. And you might be asking yourself a little bit about, like, what do you actually mean with measurements, right? We all likely know what the word means in a dictionary sense, but it's not one that's often used, at least not at a conference like Monitorama, where we generally talk about monitoring. So I want to spend the rest of this talk doing a deep dive into ISO document 9001 revision 2015. No, I'm kidding. That would be incredibly boring. But I will be using it as kind of a jumping off point, right? ISO documents do a great job at defining things and ensuring we have a common language, which I think is very important. We don't share a vernacular across the industry, can be able to talk about things. So I do think the way that ISO 9001 revision 2015 describes monitoring versus measurement, I think is actually pretty good. So let's do a TLDR. Let's do a too long didn't brief. So monitoring versus measurement, at least as defined in this sense, monitoring is essentially surveillance, right? It is watching your systems, it's watching the components of your systems, it is collecting data from those systems. It is many, many numbers, it is many, many logs, it is many, many things. And very explicitly, monitoring is defined as being over time. So monitoring occurs over a 30-day time period. You can say that your CPU utilization was, Y% at this point in time, and all that. But measuring, tells you how your system is actually behaving at this point. What are the traits of my system from an outside observer? And also, I think very importantly, measurements are explicitly right now. Monitoring happens over time. A measurement says, right now, what is going on? Right now, what is the state of my system? And more importantly, measurements aren't just about the state of your system, but what is the state of your system in comparison with the requirements of what your system is supposed to be doing, right? So monitoring collects a whole ton of data, right? You may have hundreds or thousands or tens of thousands of individual time series that you're collecting off your various different Kubernetes pods and all sorts of various, distributed systems you have, and that is useful. I'm not here today to tell you to not monitor, but the point is monitoring is just about getting all that data that you may or may not use, that may or may not actually tell you anything about how your system is behaving. But measuring via these definitions, tell you how are things actually going in comparison with the operational requirements we have. And these operational requirements can be defined in a bunch of different ways. It might be an offset, right? It might be our data is reporting X, but we don't get to actually observe this data until X plus 2, right? Like 2 minutes may pass before you're able to actually understand how things are going. And if that's the case, you need to understand that your measurements are in fact 2 minutes delayed. Otherwise, you cannot make the correct decisions. Thresholds are a thing that are often brought into place with measurements as opposed to monitoring, right? Monitoring is just data. Monitoring is just, here is my time series, here is the value at time. But a threshold can tell you, okay, but is that number that we're getting for that time series, is it in fact within a boundary, within a range, or a greater than or less than operator, whatever it might be? Is that actually relevant to how we want our system to be running right now? Measurements also include things like aggregates, right? So you can take data from many different systems, bring them all together into a single value that you can then evaluate, or combinations. You may have many different data points that all look disparate and don't really have any seeming commonality that you can all combine into a single measurement that does in fact tell you how is our system operating right now. And with all that out of the way, you may be saying, aren't I already doing measuring with my monitoring today? And you very well may be, especially if you have alert conditions, especially if you have defined, here are times that I want to be notified when my monitoring is telling me that my system is not operating how I want it to. That would be a measurement. But I think that distinctions are important. I think it's important for us to always be on the same page and kind of agree on what means what. And this ISO 9001 document, this monitoring versus measurement, like these definitions, they're really mostly used in quality management systems. So the business side of things, right? Like the orgs that determine whether or not your organization is living up to expectations. It's not a thing that as engineers we always love, but we can in fact learn things from them. And I think their definitions are pretty good overall. But for right now, let's get back to the DC Metro. So at 4:57 Eastern Daylight Time on Monday, June 22nd of 2009, Metro train 112 departed from the Tacoma station. And at 4:57 Eastern Daylight Time, Metro train 214 halted outside of the Fort Totten station. It was informed that there was a train ahead of it. A train was held up, someone hit the emergency button, and so the doors stayed open and this train did not depart. So train 214 was stalled and train 112 was approaching it. And at 5:02, train 112 rear-ended train 214 at 49 miles an hour. So how did this happen? This isn't a talk about incident retrospectives. I'm a huge fan of learning from incidents. I'm a huge fan of the concept of many contributing factors, and I could give an entire talk. We could talk for hours just about all the things that colluded, that occurred at the same time, that led to this incident happening. But that's not what I want to spend the whole talk about. So if you do care, I love NTSB reports. They are sometimes a little morose. They're sometimes a little gruesome, right? They're generally the National Transportation Safety Bureau, for those who don't know the NTSB, but like they write up very comprehensive learning from incident reports about any major traffic accident that occurs. And if you do want to go read about it, go. Document number RAR 1002. The link is here. Go find me afterwards or just Google DC Metro NTSB. You'll probably find it. The point is, I don't want to spend the whole talk on this. There's many, many different things that went wrong. But for our purposes, it kind of started here. On Wednesday, June 17th, just 5 days before, a track circuit was replaced. Now, a track circuit is not a replacement of the actual physical track line. It is a replacement of the systems that power and monitor this portion of track. But unfortunately, this replacement system, although it was replacing one that was entirely broken, did not function very well. It dealt from parasitic oscillations. Parasitic oscillations are a state that systems can get into where they report data that does not always correspond to the real world. They report good data and then bad data and good data and then bad data, right? And sometimes this is on a very predictable pattern. Sometimes it's not on a predictable pattern. But the point is, this is a commonly understood state that many systems can get into, to the point it has its own name, right? It has its own Wikipedia article that you can go read about, It's a very common state for systems to get into, and you may recognize this kind of idea from some of the own computer systems that you have been responsible for. I mean, this is essentially the concept of flapping alert. Right? You've probably at some point in time been responsible for a service that has entered some kind of state where it suddenly tells you, oh, I'm bad, oh, it's good. Oh, things are bad, oh, it's good. Oh, and some of this sends you pages over and over again, and it wakes you up at 3 a.m. and 4 a.m. and 5 a.m. and over and over and over and over again. And this kind of thing, these kind of metrics makes measurements difficult. Right? You are still monitoring your system. You're still getting the data out from your system, but you're not measuring it, because you're not actually getting a good understanding of what the actual state of the world is. And this data, in case of the DC Metro, is sent to the Automatic Train Control System, or ATC. And so the DC Metro operates with train operators. Every train has an operator at the front of the train, so they can spot things ahead of them, and so they can react. But in general, the ATC tells the trains what to do, and the train operators are just there as kind of like a fail-safe, to be honest. And unfortunately, due to this parasitic oscillation, the people in charge of the ATC had turned off all alerts from that segment of track because they could not be trusted. They were constantly erroring and then not, alerting and then not. So that was just turned off. And in a very unfortunate situation, train 214 was entirely on that segment. It did not overlap with any other segment being monitored. And so the automatic trail control system was not able to inform train 112 that there was a train ahead of it. And so it directed this train to proceed, and it moved forward at 55 miles an hour. There's also, very unfortunately in this incident, a strong bend. So the train operator was actually able to pull the emergency brake as soon as the other train came into view. But it was too late at that point. They were only able to slow the train down from 55 miles an hour down to 49 miles an hour. And this is a view from the next day as recovery efforts continued. You'll see that one subway ended up entirely telescoped on top of the other. That's how quickly they hit. And this is why measuring is so important as opposed to just monitoring. Because monitoring, again, gives you a bunch of data, and that data may be very useful. There may be many, many instances where you may, in fact, have to care about that. But measuring asks the question, what is true about the world today? What is the actual state of things in terms of my system? And now here you might be like, hey, are you talking about observability? I keep hearing this word, right? What's observability versus monitoring? And observability has become really kind of like a hip new Gartner word with its own magic quadrants and all that. And every monitoring vendor now claims that they're an observability vendor. Is that entirely true? I don't know. It depends on how you want language to evolve. But the term observability did in fact originate in control theory. And control theory is at the root of everything that we're currently talking about. Control theory has been around since the 1800s. 1863 is the first time control theory was used in an academic paper, so a very long time, more than 150 years. This is where the term observability actually came from, way before it was ever applied to computer systems. And the goals of control theory is to better define what control you may have and what understanding you may have of dynamic systems, or what we often refer to as complex systems today, which most of our computer systems also fall under. And by getting a better understanding of what control you have in terms of what can you change about things, and what you can observe about things, what can you understand about the system, what measurements can you get out of it, you can use that data to bring about better system stability. So the term parasitic oscillation that we were just talking about, right? This track control system that was entering a bad state and a good state and a bad state and a good state over and over and over again, control theory has always existed to account for that kind of stuff, right? You don't have to just say, okay, that's flapping, well, let's ignore the alerts, which is what the DC Metro system did. You could say, okay, this is flapping, so let's adjust the thresholds for what good or bad actually means. And that would allow you, using control theory, would allow you to account for that better, and perhaps that day people would still have been able to know whether or not there was, in fact, a train on that section of tracks. And all of that allows you to bring better stability into your systems. And all of this is also explicitly defined as aiming for observability, because nothing's perfect. Most of my talks are about SLOs, service level objectives, right? That's, if you know who I am, that's kind of what I'm all about. I'm not going to talk about it a ton here, but you know, it's just another great example that not aiming for perfection has really been built into how engineers approach most problems for a very, very long time. You aim for observability. You aim to be as good as you can be. You don't aim for 100%. And control theory led into control systems engineering. At least that's what's academically known in the US. In Europe, it's generally referred to as automation engineering. And by now, I hope you're starting to see some of the parallels between these very old disciplines that existed way before the concept of modern computers, especially distributed online web services, ever existed, and what we do as SRE, as DevOps, as people attending Monitorama, the things we might care about. These are very similar goals that we have. They're very similar approaches. And that's really what I want the main takeaway here to be, is that there are decades and decades of research and study from fields outside of computers that can help us better think about how we need to be monitoring and measuring our own systems. We spend way too much time in tech reinventing things over and over and over. Everything has to be invented in our... Corey's talk earlier, right? Like build versus buy. I don't know. I don't know the answer exactly when you should build and when you should buy, but we do spend way too much time building. We spend way too much time as an industry ignoring the lessons that so many other brilliant, brilliant people before us learned, even if they were lessons learned far away from software. And the problem here is that too often we monitor. I know this conference is called Monitorama, and I love Monitorama, and Measuranama doesn't really roll off the tongue, so I don't think we can rename it. But there is a distinction. There is a difference between collecting data and understanding the state of a system, and I think we need to spend more time differentiating in between those two things. Because measuring takes into account the actual operational requirements that you have. So monitoring, you install the statsd library or daemon, and suddenly you have a bunch of data like, here's how much RAM I'm using, and here's how this process is currently eating up kernel time, and you know, that's sometimes useful. Again, I'm not saying don't do that, but that doesn't really tell you anything about what your system looks like in the real world. And this is exactly the problem that the DC Metro ran into. They were monitoring their system, but they weren't able to measure it. Because if they were able to measure it, they would have been able to say, we understand where train 214 currently is, and therefore we know the correct inputs to send to train 112. But they weren't able to measure, and therefore a horrible, horrible incident happened. And there's so many more examples. So we're going to go through just a few here. And this is, again, where I love NTSB reports. On 9/44 Central Standard Time on December 19th of 2011, a Piper PA-32 plane with the tail number of N3590T crashed in Texas. This is a pretty sad story, but it's a very, very interesting one if you're interested in how systems work and how we monitor systems. And it was a small passenger plane. It was being operated by a father, his brother-in-law, his wife, and 2 kids. And they were flying from Atlanta to Waco, Texas. And they flew into bad weather. And they knew that they were going to be flying into bad weather. This was known before they took off, right? Like air traffic control, first Nashville, and then they handed off to Houston, let them know that, like things were bad. And the plane actually had, for its time, incredibly advanced onboard weather, detection and radar display. And so the pilot felt pretty confident about how they would be able to fly across the country and kind of avoid the worst parts of this weather system. But the problem is this is all on a delay. And the onboard display actually informs the pilot of how long this delay is. But it informs them of how long the delay is between once the data has been entirely collected and once it's been uploaded from the ground to the airplane. So that delay read about 1 minute. But what this does not account for is the fact that it took 5 to 6 minutes for the next rad systems on the ground to collect the data. So the display told this pilot that the weather data that they were looking at, the radar that they were looking at, the wind speeds that they were looking at was 1 minute delayed. But in actuality, it was 6 to 7, if not 8 minutes delayed from what was actually happening in the real world, what the actual state of the world was. And because of this, the operator, the pilot, made a mistake, thought he was turning around a particularly bad, weather patch, and unfortunately steered right into it. And unfortunately, that plane crashed. Because it's not a measurement if you don't know your offset. It's just monitoring. If you don't understand how the data you're collecting directly applies to the actual real world, whether or not that be a time offset, whether or not that means you have to, divide it by 100, or whatever it might be. If the data that you're collecting via your monitoring is not telling you what's actually going on, then it's not a measurement and it's not useful. Another example that most of you probably remember, a little after midnight UTC time, June 1st, 2009, Air France flight 447 crashed. This was a pretty famous incident. And although nothing was ever fully determined because you can't really know if you weren't in the cockpit at the time, but the general investigations that took over 18 months, whatever data they were able to get out of the systems, they're pretty sure that the problem was the airspeed numbers were inconsistent. So the fluid flow sensors, which is just, gas is a fluid, how many particles of air are passing through these sensors over X period of time tells you how fast the plane is moving. And these were unfortunately iced over a bit. So the sensors were not able to consistently tell the pilots or any of the cockpit instruments or any of the other automated systems, they were not able to understand how quickly the plane was actually moving. If you drive a car, you might think that you can kind of guess, right, by how quick the trees on the side of the road are passing you by. You maybe have some understanding how quickly you're driving. And I remember once I was driving through the back parts of Pennsylvania, and it was empty. And I was just driving, and suddenly my engine shut off because I hit my governor. Because a lot of cars have a governor at 108 miles an hour that will turn off any acceleration until you drop back below 100, Because I had nothing to judge from. Everything was empty. I had no idea how quick I was moving, And so it may be easy to want to try to say, well, okay, even if their sensors weren't working, they had some idea how quick they're moving. No, they had no clue. If you're up in the air, you have nothing to really judge things off of. If you're dials, if your instruments aren't properly telling you how fast you're moving, you have almost no clue as a pilot. And because they didn't know this, their automated stall detection systems also didn't know. So they pulled up at a point where they should have pulled down, and they entered a stall, but they didn't know that they entered a stall, right? And a stall is just, you know, the most colloquial way, it's a point in time where your engines on an airplane are no longer pushing you forward quick enough to ensure you're still able to establish lift in terms of the exact, you know, degrees that you're facing away from pure horizontal, right? So, but the point is, this plane entered a stall at this point, and the pilots were not made aware of it because they didn't know how fast they were going, which means their stall detection alarms didn't know how fast they were going. And next thing we know, the plane was not able to stay aloft. It crashed into the Atlantic Ocean, and 225 people died. Because it's not a measurement if your alarms can't fire. You're still just monitoring at that point, right? If you can't account for real world conditions, like the sensor's icing over slightly, then you're not measuring, you're just collecting data, you're just monitoring. So if there are a few takeaways, I didn't touch a lot on computer systems here. I didn't talk a lot about exactly how you might fix this for yourselves, and because the answer there is, you know, everyone's favorite answer, it depends. It depends on what your systems look like. It depends on what your numbers look like. It depends on exactly how you're able to measure them in the first place, whether or not you have financial constraints, whether or not you have technological constraints. But the point is, I hope, be thoughtful. Think about what you're collecting. Think about the data. Think about why you're monitoring the things you're monitoring. Again, we're at Monitorama. This is all about data collection. This is all about how can we get data out of our computer systems and into other systems that let us analyze them or understand them or alert humans or do pretty graphs in Grafana, right? Like whatever it might be. The thing though is if you're not thoughtful about what those numbers actually mean, it can lead to disaster. And you can only do that if you're auditing your data. You need to not just be collecting thoughtfully, you need to be making sure that what you're collecting is in fact what you think you're collecting. I'm 40 now, I've been in this industry for a long time. I cannot tell you how many times I've ran into terrible incidents because the numbers on my dashboard or the numbers that triggered a page or didn't trigger a page literally were not what we all thought they were. I mean, tangent that I wasn't planning on going on, but like real quick, I remember at one point we discovered, I was in charge of a large elk cluster, right? An Elasticsearch log / Kibana cluster, and it did like 350,000 log ingestions per minute, super quick, and we were running into just contention issues and ingestion problems, and I was like, okay, cool, let me go see if the network links are saturated. So I go to the dashboard that had been created years ago that helped you see, you know, all the general compute resources, right? Remember, you said CPU, you said disk utilization, network utilization. Someone had applied a divide by 1024 to all the network ingress and egress, when in fact that metric that was being collected did not need to be. It already was in megs and it didn't need to be converted. So we were off by like, you know, a huge order of magnitude. And that kind of thing can bite all of us in the ass, and it does all the time. So go make sure you know what your numbers actually are. Make sure you audit them on occasion. Assign this to someone. Make it part of sprint work if you have to. Know and double check that the data you're collecting is what you think it is. And that also includes ensuring that your data collection systems are doing what they're supposed to be doing. Because it doesn't matter if your systems are exposing the correct data and the correct metrics, if the systems ingesting them end up changing them or don't ultimately make them actually meaningful. And the biggest takeaway here is just, yes, monitoring is important. Collecting data is important. In a perfect world with unlimited resources, collect every single bit of data about every single component of every system you have, because you don't know when that might come in handy. But monitoring is not measuring. Measuring is intentful. Measuring has a goal. Measuring tells you, what is my system actually doing in terms of its operational requirements? This is not always easy. This often requires a lot of work. But I believe in every single one of you, and you can make your systems be great. Thank you.
All right, we got a few more minutes before break, so if anyone have any questions, yeah, fire them away. We got some time.
You can ask me about anything, even if it's not about monitoring versus measuring, if you want.
I think there's a question there. Yeah.
Oh, like in terms of the changes they actually made to their system? Yeah, so I think actually it was a decent effort, and we're getting into real NTSB analysis nerddom here. So I'm also happy to chat with you more after this. But the answer is that the DC Metro spent 18 months analyzing every single track circuit they had. Noticed that 6 of them were entirely fallible. Those 6 were responsible for up to 8,000 false alerts per day, which is why so many of them were just ignored. And most of those 6, including, so in my talk I mentioned that that track circuit had been replaced 5 days before that accident, but that track circuit had actually been malfunctioning for 18 months because the problem was not actually in the track circuit systems. It was part of the relays off of the track going into those systems in the first place, which is actually kind of another great anecdote to share, right? So they knew this set of tracks was not reporting the right data, so they went and they replaced the monitoring system on top of it, right? They replaced the controller and the computer that was measuring this track, but it turned out the actual problem had been happening for 18 months and was because the tracks themselves could not report the correct data. So no matter how many times they would have replaced that track controller, they never would have gotten good data out of it. But the audit, I think, was pretty comprehensive, and the DC Metro has not had a major incident since.
I think there was one other question over there. Yeah, sorry, go ahead.
Sorry, I couldn't totally hear you. My interest in SLOs or my interest in incidents? Yeah, my interest in incidents and understanding how systems operate, that's been a passion of mine for a very, very long time. I was not introduced to the concept of SLOs until 7 or 8 years ago when I was at Google. I very quickly fell in love with them because I think a very important part of thinking about systems is understanding how often they can possibly actually meet their operational requirements as opposed to aiming for 100% uptime. So yeah, now my thing might be SLOs, but my passion has long been understanding system failures, systems of any size, how they fail, how systems operate in the first place. That's kind of the root of what got me into why I'm talking to you today.
Awesome. Last call. Any other questions? Cool. Well, let's do one more round of applause here for Alex.
Hey, thank you so much, everyone. And again, it's so good to be doing some of this in person again. And everyone, stay safe.
All right, we've got one more break before our last 2 speakers. We are running on time, so 3:45. 3:45, we'll be back in here for our last 2 talks. We'll see you then. 2 talks of the day. Reminder, the after party is at 7 o'clock, but I'm going to confirm that again after these talks because I may be totally wrong. It's going to be over at Castaway. It is a short scooter ride or a lift or a not bad walk given the weather. So a lot of options to get over there. So, all right, so we're going to kick it off. Got 2 more talks and then a little bit of a break before the event later on. The kickoff, the second half here will be Harish from Meta. Let's give a round of applause for Harish.
Thank you. It's really exciting to be here. It's my actually first in-person conference in like 3 years. So pretty excited to talk about this topic, detecting silent errors in the wild. So what is a silent error, right? So the error that I've put on the screen is an example of a silent error because it just computes an incorrect value. There is no log in the system which tells you that this miscomputation has happened. There is no system event, there is no machine crash. So what ends up happening is this computation gets propagated to numerous applications within a large infrastructure, and these applications consume these miscomputations and make incorrect decisions which affect end users. So just to like highlight the scale at Meta, right? We have 3.6 billion monthly active people. So this means billions of requests every second. And this also means millions of CPUs. So when I have data corruptions which are occurring on at that rate of 1 in 100 or 1 in 1,000, we end up facing significant challenges at an application level. So I'll talk more about what is the scale we see these data corruptions at, what type of defects that I'm talking about, and why is this not a solved problem, and stuff like that. So right, silent errors, and very specifically I'm talking about data corruption within the CPUs. So these are CPUs that you would buy off the market, Intel, AMD. So these are defects in silicon. They are hard to detect, and what we've observed is that these corruptions can go undetected for months or years, and the application continues to consume these corruptions without a user knowing about it. And we have seen significant impact to services. If you're familiar with site event terminologies, this more often than not, every single CPU ends up in a SEV1 scenario for our fleet. But you might say that this is a solved problem. We have seen this before. Cosmic rays, they cause bit flips. We've also had, in the 90s, a Pentium FDiv, where it was a special function which just did incorrect results. So isn't this a solved problem? So what I want to drive contrast towards here is cosmic ray-induced faults typically occur at 1 fault in a million devices. So an equivalent odd for that is an earthquake in Seattle in the next 5 to 6 hours. That's actually a very rare event. But what we are talking about here in terms of silent data corruptions within our fleet is 1 fault within 1,000 devices. This is actually significantly larger than what we have thought these corruptions to occur at. And the odds, I've chosen a very special example here, but the Golden State Warriors were tipped to win the NBA Finals at 0.1%. It did end up happening, but this is a lot more commonplace than 1 fault in a million devices. So to explain the severity of this problem, I want to walk you through an example case study. This is a real SEV that happened within our fleet. So here we are doing a MapReduce type of operation, and we are trying to do a decompression of files. And we are in the reduce stage, shuffle and merge stage rather. And what we have here is a bunch of files which are compressed within a Spark database. So what we're trying to do here is we are computing file size for decompression. And when we are trying to decompress, do that computation, so this is an Apache Spark architecture, so we are using Scala for the computations. So the Scala math.pow function is invoked. So when typically compressed files are stored as chunks, and you multiply the chunks by the number of a power function, and then you identify where you need to put that chunks data at different points in a file. So we invoke this power function. It so happened that this landed on a defective CPU, and we were supposed to compute 1.1 times 53, but we ended up computing an incorrect result here. So what it meant was we had a check at the end of it, which was checking if the file size is greater than 0 or not. And if it evaluated to 0, we just skip writing that file. So what this meant was we had files which actually had valid data, which when we decompressed, the files were missing. So this led to like a number of holes within the decompression pipeline. And this kept happening for a month. And we couldn't figure out. So actually software engineering team spent 1 month trying to identify which machine was the root cause within a cluster which had this corruption. So as an end user, when you're presented with this problem, you just see like random holes that are appearing in your decompression pipeline. But when we started root causing this, we identified that it was actually one CPU on one core for one instruction for a particular set of data values which created this problem. Now imagine millions of CPUs across like a large infrastructure. So I'll walk through how we debug this and the timelines around it. So this software side effect is appearing for 1 month. And now I'll walk you through the process of how the entire debugging process worked. So we have Spark workload, which is in Scala. What we have here is an occasional reproduction of the issue. So every now and then your workload would randomly get scheduled on that machine. It would just so happen that there's data values which are aligned for that defect which is there on that CPU, and you would just hit this defect. So what we did was, it was a single core workload, we multi-threaded it, and on that machine that was identified by our software partners, we found that it was 100% reproducible on core 59. But it is a Scala workload, so I can't really see the assembly that it is executing on the machine. It's just too high a level language for me to decompress. And actually Scala doesn't also provide you with any tools to actually understand the assembly that it executes. So what we did was we re-implemented the Scala functionality within Java while also maintaining the ability to reproduce the defect. So again, now you have Java bytecode, and we have core 59 of the reproduction. So Java, I think everyone here knows, it's just in a compiled language. So it also doesn't provide you what assembly it executes ahead of time. There was actually a tool which is called GCJ, which attempted to do that, but it was deprecated in 2008. So we didn't have a way to identify, okay, what is happening in the CPU level. So what we did was we actually let the code run. We used the VM hotspot profiler. We had this profiler enabled within the fleet. So the code executed, and then we extracted all the assembly that it printed as part of the profiling. So now we ended up with 430,000 lines of assembly code. So once we started parsing the relevant functions, we reduced that 430,000 lines to 400 lines of assembly code. And finally, we started reverse engineering exactly what this Scala function did. So we were able to identify the equation that it uses when you're doing a power computation. This is a smarter way to do the algorithmic optimizations. There's an optimization for square, and it allows you to just compute faster if you use this formula over traditional other methods. So what we were able to do here was reduce this to a 60-line assembly. And this 60-line assembly, we integrated it into our fleet scanning mechanisms and rolled it out to the entire fleet. And what we found out is it was not just one machine. We hit more than 100, 120 machines, which had the exact same defect for the exact same family of errors. So this is an example of one defect, one CPU, one core, one instruction causing havoc within a large-scale application. And I'm here giving an example for one family, but this is something that we observe at 1 in 1,000 devices. So it's a routine practice for us to go through these kind of effects, identify minimal reproducers, and then scale it out to the fleet. So I also want to talk about why this is a hard problem within a large fleet, and give you some observations of some samples that we have seen within our infrastructure. So the first one is data randomization. So whatever defect I discover, I described previously, if you just change the power from 1.1 to the 53 to 52, it would work. So there is a very specific data points that you have to provide for you to hit the defect. There are also electrical variations. For example, we played around with all these defective parts, and we were able to identify that the device does not give the same result at different voltages, different currents, different frequencies. And there are also environmental variations, right? So as soon as we started playing around with the temperature of these defective devices, we found that it's not always giving you the accurate result at every temperature value. And there's also some seasonality that we observe within different data centers, where some data centers are more prone to this as compared to other data centers. And finally, lifecycle variations, right? So if I test a device today, there is no guarantee that I have the same accuracy for computations tomorrow. So this was actually a very specific experiment that we did, where we took a device, ran the exact same computation on it for 6 months. After 6 months, it failed for the exact same computation it has been running for the past 6 months. So this forces us to continuously test within a fleet. So just because of the nature of the defects that we are observing, we have to come up with frameworks which allow us to periodically test as well as test within a live production environment. And that's what we have built to support, to mitigate the effects of this within our fleet. So I'm going to talk about two different frameworks: Fleet Scanner, which stands for which is a way for us to do out of production testing, and a second flow which is called Ripple, which actually sits along with the workloads and then allows you to test the devices for data corruptions. And this is actually in addition to the tests that we do at our manufacturer as well as at DC Intech. So every time we put a rack within our data center, we actually put it to rigorous testing. But in spite of that, just because of the nature of defects around life cycle and temperature variations, we have to continuously test within the fleet. So I'll walk through these two flows. So the first one is Fleet Scanner. I've created sort of a state machine animation here for you to visualize what happens within a live fleet if there's a server going through this flow. So there's a server in production. And what we do is, we do my workload migration and the server is drained. And more often than not, this server draining happens because you're doing firmware upgrades, provisioning, a repair, a kernel upgrade. So you're basically piggybacking on maintenance flows, and we execute out of production testing. If the server fails, or if it fails for any of these test reproducers that we have written, we put the server in a quarantine pool, and then we run a lot of experiments on it to identify how quickly we can time to failure, or the ability to detect many similar defects of similar families. And once we establish a good confidence around it, have a good reproducer around it, which we can scale through the entire fleet, we put it through a different flow where we say it's now a high confidence signal, and we move that server to repair. Once the server is repaired, we do a verification process. The server is undrained after verification succeeds, the workload is migrated back, and the server returns back to production. So what happens within this out of production testing, right? So this is the schema for the Fleet Scanner mechanism. So there's a test repository where we keep updating with different assembly level tests, C level tests, C++ level tests. And then we put in different granular controls. You can control which maintenances you want to piggyback on, which tests are allowed for which maintenances, and what are the total time durations that are allowed in each of these phases. So then eventually, based on this kind of information, the tests are generated. The machines go through these kind of out of production testing. There are statistical models which feed into results from past tests as part of the new generation mechanisms. And finally, we also aggregate every test that has been run in the past 3 to 4 years into a result database. So the retention is significantly long so that we can draw long-term correlations. So to summarize, here we are kind of taking pit stops to run tests within a live infrastructure. We run it in non-production states. There are directed tests which are run. And the testing time is usually in the order of minutes within these flows. And we are able to achieve the entire fleet's coverage within 6 months using this flow. This is an artifact of fleet size, how often you test, how often you upgrade kernels, how often you upgrade firmware on your devices. And we've detected more than hundreds of devices. So as part of lifetime of this tool, we've been able to test for approximately 4 billion test fleet seconds. But this is still too slow across a live fleet. If I have a new defect today, I cannot really wait for 6 months to be able to clear my fleet to say, okay, that defect doesn't exist within a fleet. So what we came up with was a different flow, which sits actually with the workloads. So this is co-locating with the workloads. This is sort of a special workloads, which runs a dedicated set of instruction which has millisecond level footprint. So these are time sliced and dynamically controlled in production instances. So think of this as a service which is actually going and hunting bit flips across the entire fleet, but it has extremely low footprint so that the application performance is not affected. And the flow that we follow every time we detect a failure is very similar. Server is in quarantine pool. If it's low confidence, it goes through experimentation, multiple iterations, and then we up-level the signal to high confidence repair, and the server is undrained after a repair execution. And what's different in comparison to Fleet Scanner here is there's actually a very specialized scheduler with fine-grained control. So this actually has the ability to identify which workloads can I co-locate with. Should I run for 100 milliseconds or 10 milliseconds? Should I run every 30 minutes, every 60 minutes? So there's a way to dynamically control all of this based on which workload type and what is the pressure that is seen on the machine. So this feeds into this ripple test controller, and the ripple test repository is also like a very specialized set of tests, which are just a sequence of assembly instructions which do not create a large enough footprint on the machine that is running the workload. And similar to like last time, we put all of these results into a long-term analytics database, and we try to understand what's happening with all these defects. So to summarize, workload collocation in production tiny tests, the tests are in the order of milliseconds, and the time to fleet coverage here is 15 days. So this is what we get as a benefit of this. We cannot run tests for long, long duration like in minutes, but we are able to obtain coverage for a new defect within 15 days if it's like too targeted. And both methods of testing provide unique coverage. So what do I mean by that, right? So if you just compare the two different mechanisms here. So this data that I'm sharing is from 3 years of infrastructure testing for the entire Facebook fleet or Meta fleet. Yeah, it's actually for like one very large defect family. There are multiple defect families which we categorize based on whether it is vector type, memory copy type, floating point type. And this is for like one of the largest defect families that we have seen issues for. So one of them is performance aware. For example, Fleet Scanner is not performance aware, Ripple is performance aware. And the time to equivalent coverage is approximately 6 months for one and 15 days for the other. So this is like sort of a Venn diagram of how these coverages intersect. 70% is something that both these mechanisms are able to achieve. So in 15 days, I'm able to like get to 70% of the coverage. There's a 7% coverage which is unique to Ripple, which just comes from like being able to co-locate with the workloads. So that allows for instructions heterogeneity for you to be able to like detect a different type of corruption. And there is 23% which are just, these are defects which you can only hit if you run the tests long enough and create that kind of electrical condition. So I also want to give you some interesting observations around this. Like it's not just that first example that I showed. There are like scenarios where the number is just incorrect, right? It's not just always zeroed out. And there are scenarios where the number is supposed to be 0, but it's non-zero. And what we've observed is that these errors tend to be compiler and optimization dependent. So the issue that I described as part of the case study, if you wrote the same code in C++ or C, that you would never hit it. You had to write it in Scala. You had to write it with that appropriate optimization. And we found that even the assembly reproducer that we wrote, if we change the optimization level from O3 to O2, the assembly reproducer as well as like the C structure around it, it wouldn't hit the defect. So you have to like create that special condition within the machine for you to be able to detect this. This, as I mentioned, this also impacts computations involving non-zero operands and results. And it also affects like varying degrees of precision. So we have seen like, in the 4th decimal point, or sometimes it's just the direct number itself, which is like incorrect. And this is, something that we are like, seriously worried about because it affects like multiple instruction types, numerous types of workloads. So we have seen vector instruction types affected, floating points affected, large data moves affected. So if you're just copying files, you're thinking, hey, I'm not doing any computations here, but it actually, the copy libraries still use advanced vectors behind the compilation. So yeah, you end up just copying files and the data doesn't match from like the source to destination. It affects gather scatter operation, it affects encryption. We've seen like the numerous encryption architectures fail, and we are just locked out of like certain machines just because the encryption of that machine just happened to like land on a CPU which had defects. We've seen shared memory coherency deadlocks, and we've also seen string corruptions like across our Presto databases. So as I mentioned, it also affects cold storage applications, backups, Presto queries, kernel code. So the takeaway here is like, we are saying that it is one defect per 1,000 devices, but what we really don't know is like what percentage are the unknown unknowns. Because all we can detect is at this rate, one defect per 1,000. There are still so many reproducers, so many assembly level stuff, which could be happening in the fleet, which we have no idea, what percentage they are. So that's what we are trying to like solve using 3 different approaches. One is hardware design strategies. We are working with manufacturers across the world to like, come up with fault-tolerant designs, put a lot more priority on data protection and architecture, which actually puts a lot more value in ECC and like, fault protection logic. We're also doing specialized screening at all these manufacturers. So every time a CPU or like a component is manufactured, it goes through a specialized screening at their facilities before it gets shipped to us. And we are also looking at scale collaboration. There is no way a manufacturer would have the same scale as we do. So what we are trying to help the community with is like by providing as much data as possible around these DPPMs, defect types, defect families, and get the community to think about ways to mitigate this in design, in architecture, and also in silicon technologies. So that is at the hardware design side. In the production fleet, as I think this is probably the core of the talk, is we are doing manufacturing validation, we are doing out of production testing, we are doing in production testing, and we are constantly evaluating what it means to operate within those thresholds, pay those costs. Because ideally, I don't want to test CPUs, but we have to do it because of the defects that we're observing. And finally, we are also exploring, and we've implemented a bunch of these within our fleet, which are software and application strategies. So we've implemented a bunch of libraries within PyTorch with algorithmic fault tolerance. There are a number of services which actually run with probabilistic redundancy within our fleet. So that means 1 to 1.5%, or 1 to 2% of the workloads randomly get executed on 3 different machines, and they do an ensemble comparison to validate that the computations are same every now and then. And finally, we're also doing something called a software fault correlation. So every time an application crashes, what is the signature that I should look out for to identify if it is actually a CPU defect versus it's a software engineer's mistake. So that's actually a very hard problem. We are trying to invest and work with our kernel partners as well as software partners in enabling that. So what we are observing is with increased silicon density and technology scaling, we are more likely to see these corruptions in the future with CPUs and ASICs. And we need to build monitoring and detection solutions as a community to make sure that this is up-leveled enough for our CPU vendors to take care of it. So this is my final thought, right? It's a silent errors are like a foundational computing problem that we are dealing with just because of the silicon technology scales we're at, as well as the reliability practices we have followed in the past decade. So we as a community need to do a lot more, come together, hardware, software, kernel community, and work towards solving this problem. Thank you.
We got a few minutes for some questions. Anyone have any questions? And then just for the streamers, thank you for letting us know in the stream. If you could just repeat the question when it comes in. So yeah, any questions? Got a few minutes.
So the question is, you mentioned bit flips. Have you considered using ECC, Reed-Solomon encoding, or some kind of a check before and after an application executes computations? So the devices within a server, if you look at memory, they all come, within an enterprise application, we typically use ECC DDRs. So memory is not the source of these corruptions. And even for disks as well as storage devices, there's a bunch of encoding as well as checksum validation that happens before the data gets written into these storage devices. So what we've identified is majority of the corruptions are actually because there are too many unprotected paths within the CPU where the ECC is not implemented at all. So there are blocks which just there is no protection. There is no parity protection, there is no ECC protection, so there is no way for us to know what percentage that is. It's a trade secret with our CPU vendors, but that's where these corruptions are coming from. Sure. So when you actually identify these assembly level issues, right? I'm actually curious, if you documented the procedure, or if there are anything I can read on how you actually narrowed it down to an instruction that 60 lines of assembly. Is there something we can read to learn more about it? Sure. So the majority of the content that I presented today is published as 2 papers. The first paper is mitigating or silent data corruptions at scale, and the second paper is detecting silent errors in the wild, which is exactly the name of the talk. We do plan to someday release the exact 60 lines of assembly. I think it is almost out in the open, right? Google published a follow-up paper to our paper, and they mentioned the instruction which failed. So I guess we now have permission to release it. So I want to do it. We are working towards making it happen.
Do you think that these corruptions are a fact of life we should get used to, or are there things that the manufacturers can do to prevent them?
So the question is, do you think these are fact of life, or we should get used to them, or is there anything that the manufacturers can do to mitigate them? So there are choices which are being made, which have been made in the past decade to provide a lot more features into our CPUs without actually accounting for reliability. I think it's about to do with the type of transistors we use, it's about the type of testing we use. For example, as soon as you talk about any CPU that enables AI or ML, you're adding a bunch of bits which support like fast matrix multiply. As soon as you do that, if you don't have the cost accounted for like reliability of those blocks, it becomes a prone block for like these data corruption. So I think one way to look at this is to take a step back and look at all the features that we've enabled and start looking at which blocks need a lot more of these ECC type of protections. But at the same time, I think we won't, we will never get to a stage where it is 0 faults per million or any of that. I think that this will stay with us. What we can attempt to do is continuously reduce them by using like, testing mechanisms or by making conscious design choices. And the silicon development cycle also tends to lag, right? If you make a decision today, we'll probably see that implemented in 2027, right? So there is that delay in communication and, in just the implementation cycles. Yes.
Do you send the faulty chips back to the manufacturer? Do they do anything with them?
So the question is, do we send the faulty chips to the manufacturer and do they do anything with them? Yes. So we actually sent the faulty chips along with the reproducers and said, just run it and then you will see the defect. And they actually do integrate the tests we send as part of their testing facilities, like manufacturing flows as well as production flows. In addition, they're actually, they do a deep dive failure analysis and they give a failure report back to us. And I also want to say that it's really hard for the vendors to do this because they don't have the sequence of assembly instructions to actually hit the defects unless we provide it to them. So that's where we've been collaborating a lot. And I think Intel has open sourced a tool which is called as OpenDC-Diag, which is a tool which is available, which consists of all these like special reproducers that we have shared, Google has shared, bunch of community people have shared, and that is available for anyone to access as part of open source. But the short answer is yes, we get a lot of information about the failures.
Looks like one more back there. Straight back. Yeah.
Hello. I had a question that was related to the long-term trend analysis that you referred to. You mentioned that you guys do analysis on like a 3 to 4 year like time range, right? What kind of analysis are y'all doing at that like level of time range, and like what value do you get out of that? Because like things change a lot in like a year, let alone 3 or 4.
True. So the question is, what value do we get out of like long-term analysis? Because things change a lot within like a year or two. So when we deploy a product, it typically stays within our production for like 3 to 4 years. So for us, there's also the production deployment cycle is also like 18 months long. So let's say if I'm building a new Skylake server today, I'll continue to build them for 18 months later. So what I can gain from these long-term analysis is being able to predict if there is a need to the bathtub curve failure model. So let's say if there's like a ramp in failures that I see at 2.5 years, I know exactly what I'm supposed to do, to mitigate them or to take these machines proactively out of production. That's one strategy. And the second reason that we do long-term analysis is to identify if there is like a hotspot within the cores or within like the design architecture itself. So if you look at these in a single CPU, single instance, everything seems random. But if you put more of these together and start looking at it from a long-term perspective, you can identify a lot of trends with respect to time to failure, which modules fail, which functional units fail, and at which time in the deployment cycle. So that helps us mitigate stuff in manufacturing, it helps us mitigate stuff in the fleet as a proactive measure. Yeah.
Awesome. Thank you very much. It was great.
Thanks a lot.
I don't want to summarize that, but it sounds like that we taught rocks to think, and that was where it all went bad.
So I know you haven't seen me in a while. I wanted to shout out really quick and do a quick plug. What? Oh, sorry. All right. Wait, this is Cheslock height, though. All right. So in case you're not aware, so Harish didn't actually submit to the CFP. I found him because, if Monitorama is my side hustle, then Monitoring Weekly is my side hustle. And so I'm constantly looking for interesting articles of topics like the one Harish just presented. If that interests you, you might want to check out the newsletter. It runs weekly. It's at monitoring.love. So if that interests you, check it out, sign up. Hope to see you there. Thank you.
All right, we've got our last speaker here. Real quick, again, just a reminder, 7 p.m., we're going to be at Castaway Portland. You can search for it on Google, or if you work at Apple, use Apple Search or whatever, Apple Maps. It's easy to find. It's quick lift right away, or a scooter ride, or you can walk if you value your life and don't want to ride those scooters. Those things kind of freak me out. So yeah, really looking forward to this talk. Kick it off, Adrian.
Okay, let's try standing here for a bit. So, hi everybody, I'm Adrian Calcroft. Some of you know me as the guy that wrote that book for Sun, but with a Porsche on the front, about, I don't know, 30 years ago or something. Okay, thank you. There's a few in the audience. And then I worked for Netflix, and you probably are fed up with me talking about Netflix for most of the last decade. I spent the last 5 years working for Amazon, again, explaining Netflix to people, helping with cloud, helping with open source. And about a year and a half ago, I joined the central Amazon sustainability team. And we did a few things. We got a well-architected guide for sustainability out. I helped get the carbon footprint monitoring tool out, which I'll talk a bit about later. And most recently, there's a sustainability data initiative. There's about 100 petabytes of free data sitting in S3 that we don't even charge, or AWS doesn't even charge for using the data, like there's no egress charges and things. It's all zeroed out cost. All the sustainability, satellite modeling data you might want to need. So I helped run that, and we just did a little relaunch of that at the Remars project. So that leads me into today. I resigned from Amazon beginning of this month, so about 4 weeks into retirement, whatever you call that, which for me is going to be advising people, hopefully about things like sustainability and monitoring carbon, a little bit of consulting, and taking lots of time off when I feel like it. So that's the theory. We'll see how that works out. This is one of those talks which is kind of like a fire hose of this is all the shit you need to know. Like just to sort of blast you. So hopefully it'll keep you awake. I'll go pretty quickly through this because I've got to jam a lot of things into half an hour. Some of the talks are a bit more conceptual, but this one is just, I'm assuming you understand monitoring and you probably don't really know that much about carbon and what's going on in sustainability. So we'll go through that. So we are all collectively used to reporting and optimizing throughput, latency, utilization, capacity, maybe cost, things like that. That's standard monitoring stuff. But carbon is really just another metric for monitoring tools to report. So that's what I'm pushing here, is that eventually you're all going to be dealing with carbon as yet another metric somewhere in your dashboards. And the reason this is going to happen is the regulators are forcing it to happen, particularly in Europe. If you've got customers in Europe or you have anything going on in Europe, they have legislation that's enacted, which is happening, which is forcing this to be a topic right now that people are grappling with. They've got to measure next year and report it the year after, which means you've got to set up the measurements this year. The US is about 2 years behind that, but then everybody is also under market pressure to do more here. And you've got to decarbonize all your products and services. So how do you do that? Well, first you need to know how much carbon you're emitting and where it's coming from so that you can then go after the big bits and ignore the little bits rather than just randomly starting with the first thing you find, right? So, little question. Do you know how much carbon your company emits for, let's call it data processing and hosting each year? Does anyone here know what that number is? Any guess? I figured not. So how can you get to an answer? So how about how many dollars you spend on data processing? Just call it IT. What's your IT budget? People generally, you could go to somebody in finance and find out what your IT budget is if you don't know, right? Some of you might be VPs that know what your budget is or whatever. Let's just say it's $1 million a year you spend on IT. All right, that means you have 159 tons of carbon, which is like crazy. What? How? Well, what we've got is this economic model where you basically say, if you know how much you spent, we average the industry and we come up with an average number that if you spent $1 million on cardboard boxes or IT or jet fuel, this is how much carbon it is just based on how much you spent. So this is the economic model for carbon. and you go and get these numbers, and if you're an auditor and you come in and say, well, where did you get your carbon numbers from? You say, well, we got the number from finance, and we got this other number, which is an EPA number, so that's a good number, and it's for the right year, it's for 2020. It was calculated from 2016 data, which doesn't sound that great. And it's for use in the US only, and it tells you 159 grams per dollar, which is the same as 159 tons per $1 million, right? There are numbers like this for just about anything you might ever spend money on. You can go to somewhere, there's multiple places to get it from. Climactic.io is one of the places if you just Google these numbers. So these are called emissions factors. So the economic model for carbon, you break down where you're spending all your money, you find the right emissions factor, multiply, accumulate, and you're kind of done. So there's good things about this. Everyone uses economic models, really. Most of the numbers you see about how much carbon a company is emitting is actually from an economic model today, right? It gives you a really big picture, really approximate view. You can always get the input data from finance. These emission factors update every year, so you just got to pick the right year, the right country. Auditors can trace the calculations. This is going to be audited data. Carbon is going to be audited like money is. Right, the auditors are going to come in, the board is going to sign off the carbon number for your company. So this is going to be like financial reporting. And it estimates the entire life cycle of what it took to make the thing as well as what it used to operate it. The bad is it's a very coarse model. They're based on old data. It can be hard to find the right factor. And if you spend more, carbon goes up. Even if you spend more to reduce carbon by buying something, spending money on a low carbon thing that costs more, you'll get charged more carbon for that, right? So, and a lot of the optimizations you might think of that are cost neutral have no effect on the numbers, right? So that's not good. And then one problem is if you do an economic model 1 year, and then the next year you go, oh no, I've got real data this year, I'm going to have a better number, and I've also saved some carbon, but your numbers may go up. And that's because if you're really efficient at buying hardware and computers keep getting cheaper and faster, that means the old data from 2016 is actually an underestimate, because the dollars you spend per computer is actually going down. So, but the carbon is staying about the same. So start here, use it when you've got no other data, but everyone starts with this to do the whole company, big picture, where are the big chunks of carbon coming from? That's the economic model. Then you take those big chunks and drill in and do a process model. Before you do that, I'm going to do, so by the way, my slides, you may have noticed, have this picture of the moon gradually moving across because otherwise they looked really boring, and I had some pictures. They are nothing, the moon has nothing to do with this talk other than that I like taking photos, and I used to have a budget for making really cool looking slides, and now I don't, right? And this is what the slides looked like when I had a budget for it. And I stole these from one of the other decks I got made. So scope 1, you hear about these scopes of carbon. Scope 1 is the fuel that is consumed, and if you buy fuel and burn it in your car, or heat your house, or cook with it, that is your scope 1, right? You figure out how much fuel that is. And if you electrify everything, you can get rid of scope 1. Scope 2 is the electricity use. Technically it's the energy, but almost all purposes, just think of it as the electricity. And the things you have to think about is where does it come from? That's called the grid mix. How much is renewable, how much is fossil-based, carbon-based? And then what do you do with it when you get it? Well, if you put a heat pump in your house and put some solar panels on and some batteries and run an electric car, then you're kind of doing all the right things. And maybe you switch to an induction range, which, because gas ranges actually cause indoor air pollution and a bunch of other things. So that's scope 2. Scope 3 is everything else. So scope 1 and 2 are not double counted. They are unique to you. Once you've counted that, that's it. Scope 3 is actually double counted because it's somebody else's scope 1 and scope 2 is your scope 3. But what it means is you can't just export your problem by just outsourcing it, because that outsourcing is actually counted against you. Everything you've outsourced in your supply chain is counted as part of your scope 3 because you're influencing it by choosing who to buy and where to buy from and all of the things you do. But this depends enormously on what kind of business you're in. So let's just zoom in on data centers. So you've got grid mix, so that's scope 2 coming into your data center, comes in with some power pylons. Any fuel you burn in a backup generator, that's scope 1, okay? And then scope 3 is the data center itself, all the concrete that used to make it, all the racks and all the machines and how they were made and all that stuff that comes in, okay? If you zoom in a bit and look inside the data center, you find that power goes through lots of stages of power distribution with some losses. It's used for cooling, then it powers the racks that do the work. Okay? So what's going on is that your suppliers need to report scope 1, 2, and 3 to you, and you need to report scope 1, 2, 3 to your customers, right? So that those people in Europe, they have customers and suppliers in the US. So if you're just thinking, I'm in the US, I don't have to care about Europe for a few years. If you sell something to Europe, all those people in Europe are going to be bugging you for your scope. Even if you don't need to do it for the US rules yet, the European rules are going to spread around the world through the supply chains, right? That's the problem. And if you want to get into detail, greenhousegasprotocol.org is where you get this. So let's look at a process model. And so instead of dollars, what we're going to be looking now is kilograms of materials or kilowatt hours of energy. You measure them, find the emissions factor, same deal, right? But what we have here is something called a life cycle analysis, LCA model, which is basically cradle to shelf or cradle to grave, depending on how you think about it. But fundamentally, the supply chain for manufacture and delivery of that machine that you've got in your data center, the energy used to run it, and then what did you do when you disposed of it? Now, if you can keep machines for longer, use them for longer, say your phone or your machines or whatever, you're actually increasing the amount of use phase, and you're decreasing the proportion of the embodied carbon of how to build it and remove it, right? So the proportions are better. So you want to use things for longer, but you also potentially want to replace things with lower power devices when they come out. So you have to balance that. So great. Models are available, expertise is available, it's reasonably detailed and accurate. Energy data is fairly easy to get. In general, optimizations actually work, and auditors can trace these. Problem is, these are still averages for a business process. It's not measuring that individual machine. It's the average across all the machines in a data center, that kind of level. It's a lot of work. The supply chain recycle data is hard to get, and quite often people just can't figure out scope 3 and just leave it out, and they just focus on the energy use. And if you really focus just on the energy use, hey, I've cleared out, I've bought green energy, my carbon is 0, I'm fine, we're 100% green, and get, hey, look, those machines have chips in them that were made in Taiwan. Taiwan is pretty much 100% coal-fired electricity when they make those chips, sorry. SSDs are almost entirely manufacturing carbon. Like there's very, very little energy used to run an SSD, but an enormous amount of energy used to make one. CPUs are the other way around. It's mostly the energy used to run them versus, so lots of things here. So build LCA models, start with energy, don't forget the rest of the cycle. So how hard could it be to measure the workload of a machine? All right. So let's think about this. We've got this sort of zoomed in machine. So first of all, we get the grid mix from the local utility, comes with the utility bill, usually a month or so in arrears. But then you also, if you're a large cloud provider in particular, you have power purchase agreements and renewable energy credit purchases. I'll explain what those are in a minute. So that's the energy coming in. You've now got a mix, grid mix. Now you have the power usage efficiency. So how efficiently does that energy delivered to the machines in the data center, taking into account the cooling? And quite often, like if you're in Singapore, for example, your PUE is likely to be around 2 because it's hot and clammy, takes a lot of work to keep everything cool, and the machines aren't that clean, and the data centers aren't that efficient. If you're talking about a large-scale cloud provider data center, then it's sort of 1.1, something like that. So you can get some very efficient data centers where it's maybe only 10% overhead. But it actually depends a lot on the architecture. So what you can say is the scope 2 carbon of a workload is going to be the power mix and the PUE, the capacity you're using to run the workload, and then sort of the emissions factor for that capacity. Different emissions factor for storage or compute or network or whatever you're doing, right? So there's a few problems with this. I'm going to have to zip through this pretty quickly. Power mix. Delay. The bills are going to be delayed by at least a month. If you get into some of the developing world, it's longer than that. Power purchase agreements are contracts to build a wind farm or a battery farm or a solar farm. Amazon has over 15 gigawatts of these. I think Google has about 7 gigawatts or something. Most of the large cloud providers have somewhere in the sort of 10 gigawatt-ish ballpark amount of power that they've contracted to build, right? You pay them money, somebody builds a new wind farm. Renewable energy credits are kind of like that, except somebody already has a wind farm that they haven't contracted to sell it, and when they do the electricity, you can sort of buy the rights to the renewable energy, right? So you're just sort of paying a little bit extra to say, I'm claiming this renewable energy that you're generating, right? So it helps fund existing things. And they're basically used to top up the market. The market for RECs is much smaller than for PPAs, and it's used to top up around the edges of things to get to zero or whatever. The grid mix is getting better over time, but it changes every month. It really changes every hour, and we're starting to see 24/7, particularly from Google and Azure and FlexiDAO, who are implementing sort of a 24/7 exchange. AWS hasn't talked about this at all yet. And there's a tool called Cloud Carbon Footprint, open source, that has a bunch of estimates in it which don't take into account all these PPAs, so the estimates are really not that useful. It's useful for other things. PUE, not well standardized. It's useful to compare data centers within an architecture, but once you get to like distributed backup batteries and things, it behaves, you get different numbers based on how you've set up your data center. Capacity. Well, hey, I've used a machine. I know that's a machine. Okay, that's good, right? But I know I used an instance. Well, that's part of a machine. But what about the hypervisor? Did that get included? What happened? You know, how do you slice and dice these things? And then you get into shared services where you have no idea. Like how much Kinesis are you using or whatever, your MongoDB Atlas or something like that. You've got all these shared services that you might want to deal with. So they're hard to allocate. But if you are yourself providing a multi-tenant SaaS service to your customers, then they're going to come in and say, well, how much of your carbon footprint do you allocate to us? So everyone's got this allocation problem, and some people are going to have to go solve little algorithms that say, this is like your overhead plus this is the amount per customer, and this is how you're going to partition it out. And then we get to the emissions factors, and some of the data you can figure out, some you can't, but it depends. You've got to know what instance type it is. Is it a GPU? Is it an Intel? Is it an ARM chip? The ARM chips use a lot less power. The GPUs use a lot more, obviously. What storage class is it? Are you on tape? Tape's a really good storage class. It's basically just sit on tape. Doesn't consume very much power at all. So they're really low carbon. And there's all these other things, like what's the utilization? Like the actual power consumed by a machine increases as you make it busier. So there's a lot of confounding things in here. And some data's available for some systems, not enough, and this is the real problem we have right now. So what can you do today? So look at the moon is great. Basically, I set up a camera outside with like my phone hooked up to it and pushed the button every now and again so I didn't have to go out in the cold, so the moon sort of gradually worked across. So if you're trying to report something that's going to be audited, like your board's going to sign off on the numbers, you've got the cloud vendor reports, on-premise economic models, and these are sort of more accurate in some sense, but they're less useful for tuning, right? They're accurate in the sense that the auditors will sign off on them. So this is the kind of state of the world for cloud vendor reports. AWS is this customer carbon footprint tool. It's part of the billing console. You just scroll up in the billing page and you'll see a bunch of stuff about carbon. If you're a pretty small account, you'll just see zeros there. If you're a fairly large customer and if you have stuff going on in Asia, you'll see it quite a lot more. The European, US, this is really just scope 1 and 2 as well. We don't have any of the supply chain figured out for AWS and most of the other vendors either. US and Europe, and Europe and US based regions are pretty close to zero right now for pretty much all the cloud vendors. The numbers are reported a bit differently here and there, but that's kind of what's going on. Asia, it's very hard to buy PPAs in Asia. It's very hard to source green energy, renewable energy. So that's when most of the work is currently still happening. Azure, there's the Microsoft Sustainability Manager. It's part of their Dynamics product, which is a commercial product that you pay for, and I don't think there's a free thing they have. Maybe there is, but it looks pretty much like they're pushing people to go pay money and use Dynamics. High resolution, like the AWS data is very low resolution. I've left now, so that you're still hassling them to release more data, right? So that's kind of what's going on at AWS. Azure already has very fine-grained data out there already. These are both market-based, and I'll explain what that means in a second, but GCP is using location-based, and the numbers just aren't comparable. It's a totally different way of calculating the carbon, but they have a nice API and a tool and a lot of data. So if you're going to build a workload optimization product or a service that sits on top of that carbon data, really, Google's really the only place you can do it right now. They have an API and lots of data, you can go do it. There is no API to the AWS stuff, and it's not high enough resolution, and the Microsoft stuff, you're kind of getting into how do you hook data out of Dynamics or something like that. So market versus location. So CO2 is globally mixed. If you measure CO2, anywhere in the world other than sort of, in general, it mixes very clearly. So if you save some carbon here, you can emit carbon somewhere else, and it offsets in terms of the total carbon in the atmosphere, right? So that's the idea of like offsets. But as we get better and better at reducing carbon, what we actually have is that the easy to reduce things gradually get used up, and we end up with the difficult places are left. So it actually is better to do the more difficult ones and start working on those now. Otherwise, we won't have time to fix them. So a power grid is a market for energy. And if you remember that Texas having that big freeze-up thing they had last year, whenever that was, that's because Texas is an energy market and they don't interchange power with the rest of the US. There's actually 3 energy markets in the US. So what that means is if you do a PPA to build a wind farm in Texas, somebody somewhere will shut down a coal-fired plant or a gas plant because the power is in Texas. Right, so that's what's meant by a market-based sort of accounting. So what you're looking at is because you have, say, a data center in Texas, you have the energy you buy in Texas that goes into the Texas grid counts towards that one, but it doesn't count towards what you're doing in Ohio, for example. Right, so that's the market-based thing. And some people kind of take a global market. That's kind of Google have been talking about that for a while, but they're getting now to something even more local because they're looking at hourly data by location. So again, the Google location data, by the way location is defined, you can't include your power purchase agreement, so their data comes out differently. So it's just a mess right now, sorry. This is there's an interesting, if you go look on the Google site, they've got something. This is generally what you'll see around the world in terms of grid mix and time of day things. The interesting thing, if you look at Singapore, it's only 3% renewable energy in Singapore. Singapore is too small to have lots of solar panels and wind farms. There isn't enough land. And they have basically dirty energy in Singapore, and everybody has that problem, right? This is not, the map for Azure and AWS would look very similar with different regions in slightly different countries, but it really looks very similar. Asia's the problem, and we're going to be fixing that in the next 4 or 5 years, I think. All right, so if you're trying to do something here and you want to optimize a workload to reduce its carbon, how are you going to do that? The stuff you're getting from the vendors isn't that useful, but there's this thing called the Cloud Carbon Footprint Tool. There's a thing called SCI from the Green Software Foundation, and these are not accurate in what, don't believe the amount of carbon they tell you, but they are directionally, proportionally good. So if they tell you they're saving 30% of your carbon, they probably are, but the actual tons of carbon will be wrong, right? This is what the Cloud Carbon Footprint Tool looks like. So I would use it for tuning exercises within a region. It does produce things that try to compare. I mean, it attempts to compare cloud vendors across regions and across vendors. It's just that it doesn't know the PPA data, so it's just the numbers are just wrong. And they don't have a way to fix that now. As more transparency comes out from the vendors, maybe after a while, we'll be able to calibrate that in, but that's really the state of the art. But within a region, if you're trying to tune a workload, this is a good tool. Okay, Green Software Foundation, the idea here is that you have carbon per API call or per transaction or per unit of work, and you can start figuring out that as a metric to actually report into your system. So it's kind of trying to get that fine grain unit of work, kind of mile per gallon kind of level of detail. So just some opinions across the cloud providers. I don't think right now there is that much difference. You shouldn't really be thinking about moving a workload between cloud providers just to reduce carbon. They're all roughly the same in a region. Everyone's got a problem in Asia. The rest of the world, it's pretty much low carbon already. And The scope 3, the embodied carbon to make a machine, it really doesn't vary that much. You've got the same RAM and CPU in most of the systems, right? But there's big differences right now in tooling and transparency. AWS is the least transparent. Google's got the best tooling. There's just huge differences. And I think over time, these things will gradually come in. But right now, there's a lot of customers that are going to want an answer. So if you're a monitoring tools vendor, I think there's a lot of opportunity here to just gather this big mess together and say, okay, we're going to come up with some numbers which we can try and come up with. If they're auditable, that's good. If they're good for optimization, that's a different workload. So I try and separate sort of what you want to do for audit from what you want to do for optimization. So hopefully that was a useful intro. DM me or whatever if you've got questions. I'm going to be around through the end of Tuesday. So happy to talk to anybody about this. And now I guess we're kind of done and you can go and enjoy yourself for the evening. Thank you. Any Q&A? Looks like we have a few minutes.
Yeah, we have a few minutes.
Yeah.
Clarification question. So when you say that a lot of US and European cloud providers are carbon neutral, does that include scope 3? So
No, this is just scope 2, it's energy use. So over the last few years, all the cloud providers have been buying gigawatts of power and more batteries so that you've got storage to carry you overnight. But lots of solar, lots of wind, and that has neutralized out the grids, what was remaining in the grids in different countries. I mean, if you look at France, it's like 90-something% nuclear energy, so you don't need to do much to zero that out. Similarly, Sweden's pretty good, the UK's pretty good, in somewhere, Dublin or Spain or whatever, you put in the solar and it zeroes it out. So these kinds of things have been dealt with. And last year there was still a fair amount of work to do. This year I think we're pretty much reaching the point where just about everybody, when you do that little carbon report on AWS, you're going to get zeros most of the time in US and Europe for your carbon footprint. But that's in the market-based model, not taking account of time of day. Right, so they're generating extra power during the day, and they're using they're using power at night. So there is still carbon being used, but that's kind of where we are right now in terms of the sort of state of the world. More questions? Yeah.
I'm just wondering, you're talking about data centers, but when companies, for example, do a lot of traveling or flying around the world, how does that come into this?
Yeah, so they're talking about travel. If you're looking at different companies, I have one example, like a couple of extremes. I did a talk on the well-architected guide, and we had Starbucks come in and do a little section in there. I think from memory it was about 1% of Starbucks' carbon footprint comes from IT. 20% or something comes from milk, right? So if you want to help save the world, drink oat milk. Oat milk lattes, whatever. Switch to oat milk at Starbucks, it'll help them, right? So what you find is like 99% of Starbucks' carbon footprint is the physical world and 1% is IT. If you pick, say, a SaaS provider that just does nothing and is a fully distributed organization, doesn't have any offices, pretty much their entire carbon footprint could be their cloud bill. Right? So you've got to figure out where are you in that extreme or somewhere in between, right? As soon as you have any physical things like buildings are a big chunk of the carbon footprint. So if you're a SaaS provider with an office, that office is going to be most of your carbon footprint. Travel and transport is a big category as well. Flying one person to Europe is about a ton. I think a round trip is about a ton. So think of that as sort of what is a ton of carbon? It's a round trip to Europe. It's like 1.5 tons or 3/4 depending on where in Europe and US you started. But it's order of magnitude, that is a ton of carbon, right? And we're trying to get to sustainable jet fuel based off green hydrogen that's generated through electrolysis, and then you can sort of fly for less, right? So that's what the airline industry is working on right now. So yeah, travel and transport will quite often be a large component, but proportionately it's probably smaller than buildings for most people, and commuting and all these things. So all this work from home stuff is helping the planet a bit, but then people are going on vacation more. So I don't know. You gotta take it where you can. Got one more? Yeah.
Okay, and we'll get you next. Go for it.
For the legislative or policy forces, how do you think the European stuff is going to have more effect than the new SEC rules, or where do you see those taking?
Okay, so the European rules came into effect. They were signed in last December. You have this year to figure it out. You have to measure next year, and you have to report it in 2024. And this is on the books, right? So these are decided. What's happening in the US right now is the SEC is looking at some similar rules, which are going to be different, just to make life interesting, but are going to be similar. But so if you operate internationally, you're going to have to figure out how to do both kind of rules. And the details of why they're different, but it's sort of, think of it as sort of the US is doing sort of a bottom-up what's practical approach, and the Europe was doing a top-down, this is what the world needs approach. So they're sort of meeting in the middle, mostly the same, but with some detailed differences. So the US is probably 2 years behind, but like I said, the supply chains of Europe are going to touch the world faster than the US sort of gets its act together. So the large corporations that are international are all scrambling right now to figure this stuff out.
There was one up top there.
One up top, yeah.
As the corporate trade and the energy consumption becomes more of a forefront, do you think that this will cloud provider will start charging for energy use? Is it definable to that remain abstract away?
So the question was, will the cloud providers start charging for energy use? In general, the PPAs are cheaper than buying energy on the open market. So the cloud providers are getting a discount by buying renewable energy. And that's just, then there's no separate charges. If you want to get into a bit more detail, the well-architected guide had some ideas in it about not running your cron jobs at the top of the hour at the same time, because that causes a big spike in load, which causes you to need more capacity. So you should jitter your cron jobs around and things like that. But there are some ways that you can help the cloud providers not need so much capacity and move things around. You know, you could think about playing games like biasing the spot market to use less carbon or something like that. But those kinds of things are sort of still speculative. And Google's got some things where they do sort of follow the sun. You want to run your training workload, your big GPU training workload, wherever it's sunny because it uses less energy. But then you have the capacity still sitting there burning energy. Like just because this GPU is not being used to run your workload, it still exists. So most of the carbon is there anyway. So it doesn't make a huge amount of difference to do follow the sun. I would just run your workload where you need to be. And in the next few years, all the cloud providers will get green energy everywhere in enough volume that it won't be an issue.
I was going to say there was one more question here.
Okay.
Yeah. So from an auditing perspective, using the economic model of there's some multiplier of what you're using, is there any value in being more granular in that end? Instead of just saying how much you spend on cloud, like this is how much you spend on networking or on egress or some very specific pieces, and saying it's more expensive to do networking from a carbon perspective, just in an auditing sense.
Yeah. Yeah, so the question is, can you get a bit more granular with the economic model? If you can come up with differences across your suppliers, but you can still use dollars as the denominator, if you like, right? But then you can basically say, okay, if I'm buying delivery services like Amazon does, there's UPS and there's the Amazon-owned delivery, and then there's like UShip or whatever, right? There's all these different delivery services. They probably each have a different carbon level per dollar, and we can just still use the dollars to do it, but we figured out. So you can derive your own emissions factors, or you can use the industry standard ones for the standard stuff. So what generally people do is a combination of that, but then you get into the process model where you really want to know how much fuel was burned by your delivery fleet, rather than how many dollars you spent on it. Yeah. So it gets complicated. Like the mathematical model here is you multiply two numbers together. It's not a hard model. The problem is understanding which two numbers to multiply together is ridiculously complicated. and people do it wrong all the time. So there is a lot of revisions go on in this space, and there are people that specialize in this. And if you want to get into the complexities of it, there's some real interesting stuff. If you look up LCA modeling, life cycle analysis, it's an interesting area. Okay, thank you.
Awesome. Yeah, thank you very much. Really important topic. Awesome talk. Thank you so much. Round of applause.
All right, how about another quick round of applause for all of our speakers today? It was a fantastic day.
Also, a round of applause for our amazing interpreters here, working extremely hard.
There's some inception about, like, actually.
They have to sign their own praise.
Yes.
Exactly.
Did everybody have a good time today? Honestly, I really enjoyed the lineups today, the talks today. I thought it was fantastic. I'm not going to lie, though. When I saw Adrian's submission, I thought Graphite was making a comeback, but yeah, next time. That's all right. Still a good talk. Okay, if anybody missed the announcement, after party tonight, 7 o'clock, Castaway. I left directions in the general channel.
It is an indoor and outdoor event, so if those are concerns, there's a great outdoor area. There's also an indoor area. I think it's actually kind of open on the indoor.
Yeah,
so.
yeah. It's actually, if you've been to previous events, I think we were there in 2019. It's a fantastic venue. It's very kind of open. We've got all kinds of games. We've got other things going on. We'll have a churro truck with ice cream sundaes or something. I don't know. It sounds pretty cool. Anyways, thank you all very much. I had a great time day one coming back to Monitorama in Portland, so y'all were a big part of that. Thank you very much, and can't wait to see you tonight and tomorrow. Thank you. So, moving